Что-то происходит.
Это мы.
Это мы, да.
Это мы. И есть еще криминал.
Надо еще понять с микрофоном. Колонки. Включили?
Звук есть, а
Колонки включены. Да, это ничего. Давайте сейчас я выйду, если есть хороший, то вы как-то пусть на меня.
Окей.
Так, это, наверное, какая семечка.
Да, слышно,
Сейчас нас слышно?
Нас же тоже слышно. Мы же даже вернемся, скажем, что не слышно.
А вас не слышно, потому что нужно снять установку. Надо ее, наверное, включить как-то. Ну, какой-то у вас есть шум.
Может, еще где-то не здесь у меня. Здесь не здесь у меня. Значит, мне казалось, мы как-то более сложно уходили, но в этом были все то же самое. Какой, да?
Ну, как же это сделано? Так, давайте проверим. Раз, два, три. Раз, два.
Аудитория там есть ситуация, когда
Добрый день.
Так, что же, может быть, вот эти вот подавления. Так, динамик и интересуемся. Так. Как тут с этого? Так, динамики, лайн.
Мне нормально слышно вас. Это хорошо было.
Сейчас хорошо?
Мне кажется, да.
Если ничего нет никакого шума, все нормально, да?
Да.
Я все слушаю.
Что случилось, что вы сделали? Да, непонятно, что мы поменяли. Вроде ничего не трогали.
У вас нормально?
Да. Более-менее. Здесь, конечно, куча мороки с этой техникой. Это в смысле у нас. Одну из комнат открыли. Ну да, да. Ну да, это не самое удачное расположение. Здравствуйте. А нас слышно?
Юра, вы толстые стали.
Какой я стал?
Толстые стали, говорю.
Наушник?
Толстые стали.
Из-за наушников или просто
Да.
так?
Я не слышу.
Почему? Не слышите?
Почему-то нету. Звука нету. Вы меня слышите?
Да, слышу.
Я вас не слышу совсем.
Очень
Вообще,
странно.
подожди. Все, я сообразил. Да.
Теперь слышно?
Вот сейчас звук я поставил, да.
Прекрасно.
Приветствую вас.
Эхом небольшим было слышно.
Все, я звук поставил.
Или может
Прекрасно.
подразделение шумов там или что-нибудь? Или нормально, все четко слышно?
Как, Евгений Ильич,
Добрый
ощущения?
день, Юра, рад видеть вас.
Взаимно, взаимно, взаимно.
Что-то не
Я могу
самые
сказать,
ранние.
что хорошего человека чем больше, тем лучше.
Интересно. Это интересно, да.
Да. Иджат Хакович, у вас что там, доска дома, что ли, стоит? Вы же из дома?
У меня доска, да. Я же занятия веду.
А, понятно. Вот несчастный человек.
На этой доске я пишу.
Иджат Хакович, рад видеть вас.
Да, взаимно, да. Так, вот я вот голову вижу, вот поднимите, пожалуйста, вот я волосы вижу, во. Хорошо, да. Вы где находитесь, Женя?
Я в Барнауле, дома.
А, дома, ясно.
Тут мне это вакцинацию сделали дважды, и я это самое. Никуда пока не хожу, по большому счету.
А я пока избегаю вакцинации.
А, какой хитрый.
Знаете, есть такой анекдот, Карикатура такая есть. Две мыши встречаются, одна говорит другой: ты сделала вакцинацию? А та говорит: нет, еще на людях не испытали.
Ну, сейчас уже более-менее. На мне уже испытали.
Так.
Жить можно.
А вот Даня, кто такой Даня, интересно?
Не знаю.
Вот Даня есть написано. Даниил тем самым должен быть. А кто у нас Даниил, не знаю.
Но я думаю, нам скоро звук придется отключить, чтобы не мешать народу, да?
Да, это очевидно. Это маленькие мгновения,
Какое мгновение, какое.
редкие.
Ага. Так, ну ладно, хорошо. Пусть я по наводке Виктора Александрова попал на это самое вот, то есть на нашу встречу, потому что я не знал, как там включиться. Он мне написал, и все сработало, видите, хорошо, да.
Ну, замечательно.
Так, Юра, а вы тоже сам у себя находитесь?
Да, конечно, дома, видите. О, как.
Да.
Ну, у меня доски нет, я же ничего не преподаю, нехорошо.
Что-то черное есть сзади вас.
Это кресло.
Нет, квадратное есть, вот, я вижу за креслом.
За креслом? А, ну это шкаф книжный.
А, это-
Большой. Книжки я еще читаю.
Юра, это многообразие с особенностями.
Ну, что сделаешь? Без особенностей тут никак не обойтись.
Особенности разные бывают, да.
Ах, хорошо.
Ну, вот видите,
Так.
чудеса техники, да.
Ага. Ну, я так полагаю, нам уже пора отключаться. Тут уже
Да, да, вы правы.
звук, по крайней мере, да?
Да.
Ну ладно, еще поговорим. Там же есть какие-то
Остается
совещательные комнаты.
Ну ладно, да.
А что такого? Кошка нормальная.
Да.
Не знаю, список участников нам надо сбоку? А, вон он сверху. Правда, не...
Какие-то избранные участники?
Ну, наверное, самый громкий.
Если ничего важного вещать,
Наш микрофон выключить?
зачем?
Так, ну что ж, зал мы видим, да. Так, вот так. Что-то ленинградцев не видно никого, да.
Иджат Хакович, а у нас приказ ректор издал, согласно которому кто не провакцинировался, тот не может работать.
Да. у нас тоже такой приказ есть.
Вот. И пришлось пройти вакцинацию.
Да, ну вот у нас тоже есть такой приказ. Даже, по-моему, я работал, дистанционно работал, вообще говоря, весь год предыдущий. Ну, сейчас тоже, ну, не знаю, в общем, я пока не собираюсь вакцинироваться, не знаю, мне это очень, скажем так, боязно. Куча всех болезней, неизвестно, как они себя поведут после этой вакцинации. Я поэтому пока не выгоняю. Ну, я еще пока в отпуске, поэтому не выгоняют еще пока.
М,
До
Понятно.
29 августа я в отпуске, поэтому пока выгонять не будут. Ну, а дальше посмотрим, что будет. Вот есть вакцинация, вакцину, экивак корона, говорят, хорошая, легкая.
Может быть. Ну, мне вот первый укол сделали, все нормально было, я даже никакой реакции. А второй, долго рука болела, и где-то дня 3 было 37,6, 37,5, вот так вот.
Да.
Ну, я им позвонил, они сказали, какие таблетки принимать. Вроде это самое, 3 дня прошло, я попринимал, ну и прошло все это. Другое дело, какие генетические последствия будут, Бог его знает.
Об этом мыши и говорят.
Да.
Да. Какие там через несколько лет что будет, непонятно. Ну, генетически, скажем, нам уже поздно рожать детей. Да. Только на нас самих отразиться. Ну, Юра еще может, Никаноров.
Ну, кстати, ковид влияет на деторождение,
Да,
по утверждению специалистов.
да. В смысле, способствует и наоборот.
Бог его знает. Влияет, это же не означает, способствует или нет.
Да. Вот влияет по-разному, может влиять. Да.
Хотя, конечно, это очень ценное замечание. Вы, как всегда, зрите в корень.
Да. Да.
Так, это что выскочило? Ага, программа.
Программа, да.
Да. Я ее открыл на всякий пожарный. Ага, ага. Ну, совпадает полностью.
Да. Все я вижу, эти самые темы все не отрицательные, кривизны все. Положительно, отрицательно, да. Хорошо, посмотрим, что будет. Да. Так, осталось уже 15 минут осталось. Вильгельм, да?
Привет.
Good morning, colleagues.
Привет. Салют.
Салют. Ага.
Good time of the day.
We have almost 14 of 2 afternoon p.m. in Novosibirsk.
Hello. Хорошо. Thank you.
Ага.
Вильгельм,
Да,
now you can speak Russian.
да.
Да? Да, я.
Ja, ich kann etwas Russisch sprechen.
А,
Ich kann etwas.
Sehr gut, sehr gut.
Dankeschön.
а,
Schöne Sprache.
у нас время есть. Вы понимаете меня, Вильгельм?
Да, я все
Да.
понимаю.
Ага. Я недавно вычитал из биографии такого немецкого, ну, наверное, математика. Его, он, Хакан его фамилия, он энергетику изобрел. Energetics. Так, что я про него прочитал? Его дед участвовал в Первой мировой войне, попал в плен к русским, выучил русский язык. Да. Его отец участвовал во Второй мировой войне, попал в плен к русским, выучил русский язык. И мать этого Хакана сказала: выучи русский язык на всякий случай.
Wonderful story.
Да, видите.
К счастью, не пригодился.
Сколько часов вы сейчас в Москве?
4 часа с Москвой у нас.
Да, хорошо.
Вот.
Не 3 часа разницы.
4.
Ага.
И Виктор Андреевич Топоногов жил здесь, в Новосибирске, в 4 часах от Москвы.
Да.
Нет, Володя, немножко не так. 4 часа было в советское время. А потом...
сейчас тоже 4 часа, Эджак Хахович, уверяю вас.
Потом стало 3 часа.
Нет, 4, это в Омске 3.
Никогда не было 3 часа?
Было вот когда. В 50-х годах, когда в Новосибирске не было моста через Обь, левый берег Новосибирска был в 3 часах от Москвы, а правый в 4. Но это было 60 с лишним лет назад.
Нет, в недавнее время не было 3 часа?
Нет, у нас 4 часа по-прежнему.
Да? Интересно, я как-то считал 3 часа разницы. С чего это я вдруг такой решил?
Евгений Дмитриевич, good afternoon.
Good time of the day, Владимир Петрович.
Ну, вы в Барнауле?
Yes, of course.
Вот.
Dear Wilhelm, sorry, Владимир Петрович. I have some
понимает
questions.
По-русски.
I see. Your father wrote a book with Detlef Grommel and Meyer.
Да.
Detlef Grommel and Wolfgang Meyer.
Yeah.
Are there Toponogov conjecture on complete?
No. Okay, no. Okay.
No, in this book.
Toponogov conjecture is in classical differential geometry. The solution is not in classical. But however, the statement of the conjecture is in classical differential geometry, in surfaces, in classical surfaces. While this book is in Riemannian geometry.
Yes, I understand.
Some global story. So, yeah.
Yes.
Yeah.
It's a famous conjecture.
In fact, not.
Not?
Yeah, no. So in fact, I don't, okay. The most famous work of Viktor Andreevich Toponorov was in Riemannian geometry and metric geometry.
Yes.
Only later in his life did he look at, after 1990, did he go into classical differential geometry. And he wrote a very nice book. And this conjecture, in fact, is not so famous. No. We discovered it, in fact, by accident. When I was in China, somebody told me. It's a beautiful paper, of a very deep paper and good paper of Toponorov, but it's not even quoted a lot and so on. But our solution, in fact, sort of mirrors a little bit the arguments that he gives. So it's amazing. So our solution will be not in the framework of classical differential geometry, but in some higher dimensional space. In a four-dimensional space. We sort of lift the surface from classical surface to a surface in four-dimensional space.
Interesting.
And then just work in four-dimensional space. And of course, this is not something that Toponorov considered. But he had, of course, amazing intuition, and he felt something going on. It's clear from his paper.
Вильгельм, я по-русски расскажу о Топоногове одну историю.
Окей.
Он очень хорошо играл в карты в игру под названием «Преферанс». Такая популярная в России игра. Там надо много считать, комбинаторика всякая. И он мне как-то... Я никогда с ним не играл, но все говорили, что он играл замечательно. И он как-то мне сказал, что в преферансе мало считать, вот какие карты вышли, какие у тебя на руках. Надо еще вот чего-то такое вот чувствовать вот каким-то там шестым, седьмым, восьмым.
Интересно.
Надо иметь карту в рукаве.
Нет, он еще под это дело. Когда он в 70-м году защищал свою докторскую диссертацию, я как раз в 70-м поступил в аспирантуру к нему и числился его аспирантом. На его защите я обнаружил, сидели в заднем ряду 5 примерно человек или 6, которых я на семинарах геометрических не видел ни разу. Я спросил, а это кто? И мне Шефель Самуил Зусевич, его друг, сказал, это преферансисты. Пришли поболеть за партнера.
Партнеры, да. Так, ну что, времени еще... Так, сколько времени уже?
Без 5.
Без 5, да. Так.
Ага.
Hello, everybody. If you can hear me.
Hello.
Hello, hello.
Thank you very
Good
much.
afternoon, Виктор Алексеевич.
Здравствуйте.
Ночь, правда.
I'm glad to see you.
Да, я тоже, спасибо.
To see you too.
Надо звук. Да, и может трансляцию вырубить.
А зачем?
Ага.
Пока программа вот.
Что, а смысл-то? Нет, а там транслируется все равно самое сильное, а не то, что мы здесь поставили в центр. Что? Окно еще закроем, а то шумно. Так, здесь уже пошло расшаривание экрана. Отлично. Ну что, начнем?
Еще 2 минуты.
Разве?
So, welcome everyone. I hope everyone here hears what I say. Let us begin our conference dedicated to 19 years from Viktor Toponogov's birthday. Actually, 19 years of Toponogov was 2020, last year, and the conference was planned last year, but the world went crazy and we decided to reschedule it to 2021, and then the world is still crazy now, so now we have this hybrid mode event where about 2/3 of participants are online and 1/3 is here. Let me explain some of the technicalities. So Zoom talk, we will have, of course, remote users of Zoom as usual. And here we will have 2 Zoom users. One Zoom user is this entire room. The camera is there and the microphone is here. So either you are talking with people by your back head or you speak to them face to face, but the microphone is upstairs. This is for people here. And the second user will be called Lectorium. He will appear when someone speaks here in person. This is equipment that will be used there. So in this case, it's remote people should switch. Well, if it doesn't switch automatically, then you should look at Lectorium user. We have breakout rooms. You can check, the remote users can check in your Zoom interface. There is a kind of square split into 4 squares, breakout rooms. In Russian it would be сессионные залы. These are virtual rooms where you can meet in small groups. If you try to push this button, it will show which breakout rooms are there. There are 10 ones. We can create more if needed. And 2 of them are actually connected to physical rooms here in Euler Institute. We suggest that online speakers spend some time, if they like, of course, in breakout rooms after the talks, not immediately, but the nearest coffee break or dinner break or whatever. So just if you expect some semi-private discussion of your talk, or maybe some questions during your talk requires more elaborate answer, you can move to breakout room. It's easy, intuitive interface how to move it there, and other people can go there and discuss the details in parallel with other stuff. So it is not necessary to discuss everything in a single Zoom session where what you say is heard by everyone and you cannot have small talk in parallel and so on. That's about breakout rooms. Next, the next technical detail is we have YouTube translation. And if you miss the talk due to time zones or whatever, you can find recording later and maybe even comment on YouTube, but we do not promise to keep track on comments in real time. Well, also, Zoom chat is not, oh, okay. Something we've forgotten to record the talks. Also, Zoom has the feature of chat, but keep in mind that it disconnects sometimes, and when someone disconnects and reconnects back, then the chat is lost for that people, so it's not a good means to communicate, but you can kind of chat in private using this chat. So pushing chat button right to specific person, then maybe suggest to go to breakout room 5 and so on and discuss something. So that is a good idea. Where we expect questions by voice. Reading is a complicated option. So let us begin with this. All this technical setup is kind of experimental. The organizers have little experience in this type of operation, so we apologize for any glitches that might occur. And let's begin. Maybe it's 5 minutes yet before the scheduled talk. Wilhelm, are you with us?
Yes, thank you. Yes. Can you hear me?
So, well, maybe we should make this погромче сделать slightly. Can you say?
Yes. Can you hear me?
Yeah, great.
Thank you.
So, well, I don't know if we should wait that extra 5 minutes to be on the schedule. By the way, yes, we have to take care about time zone difference. The time now in St. Petersburg is 10 a.m. and 7 minutes. And our first speaker is Wilhelm Klingenberg from London. As far as I understand, you are in St. Petersburg or no, I don't know. But still have to speak online. Well, that's okay. We will test all possible options. So let us begin.
Thank you very much. Have you shared the screen? I shared the screen.
Yes, we can see it.
Yes.
Thank you.
Great.
So the title of my talk is Toponogov Conjecture on Complete Convex Surfaces. The talk is dedicated to the memory of Viktor Andreevich Toponogov. And let me also take the opportunity to honor the memory of Stefan Cohn-Vossen, who was interested in this subject, global classical differential geometry, and who passed away 85 years ago in Moscow. This is joint work with Brendan Guilfoyle. So let me cut to the chase and start in the middle of the construction before going back and giving more detailed definitions. The main item will be LR3, which is the collection of all oriented affine geodesics L of Euclidean 3 space. Next, this set is well known to be parametrized by the total space of the tangent bundle of S2. So a point in this collection will correspond to a point in this total space of R2, of TS2. Consider an oriented geodesic of R3 that will give rise to a rotation by 90 degrees, which is an isometry of R3. This map takes lines to lines and thereby induces a map of this collection of lines, TS2, fixing the very geodesic about which we rotate. Now, we have a smooth structure here for this collection, so it's the linearization of this map. This map will be differentiable in terms of that smooth structure. The linearization of this map at the fixed point L will be an automorphism of the tangent space at L of the collection and will indeed give a complex structure on the total space TS2. Here's now the passage that we will undertake in addressing this conjecture of Toponorov. Namely, an oriented classic surface of Euclidean 3 space gives rise to a particular subset of the collection of all geodesics, which we denote by NP, and that will be the collection, the subcollection of all geodesics passing through all points of P and being normal in respect of the orientation to P. This subset is two-dimensional since each point of P will have one normal, oriented normal. So we may view this NP as a two-dimensional surface in the four-dimensional space TS2. So here's the picture. LR3 is the collection of all oriented geodesics, and J of L is the linearization of the rotation in a counterclockwise direction, or in a positive direction about L in R3. So throughout, we will switch and view NP both as a family of lines in R3 as well as an embedded surface in TS2. Example, let capital S sub P in R3 be a round sphere of any radius centered at a point P in R3. The collection of normal lines, L, to this round sphere is identical to the collection of all oriented geodesics containing the point, the center, P. Note that this collection of lines, subcollection, NSP, is invariant under rotation of ambient space R3 about any of its elements L. So that is saying that this surface, N S sub P, viewed as a surface in TS2, is a holomorphic curve in TS2 comma J, which is saying that for any point L of this surface, J leaves invariant the tangent space to that surface at L. So this is a misprint here. This should read on the right-hand side, TL N of SP. So here you go. Here is a surface P. Here is the collection of its perpendicular geodesics, NP. Here is a round sphere centered at P on the left in R3, which lifts, if you wish, to this collection N, that should be N rather than L, SP in LR3. Notice that every unoriented line in this collection is covered twice by two elements of LR3 in opposite orientation. Now, the main observation is that a point P on a classical surface is umbilic if and only if the collection of its oriented normal lines, NP, is rotationally invariant up to order 2 about the normal L of P. So I apologize, the surface would be rotationally invariant up to order 2 about that rotation. NP will be invariant under J up to first order, since we lose one derivative in this transition, which is saying that this point L is a complex point of this surface NP. Here's the Toponogov conjecture. There is no proper convex embedded non-umbilic surface P sub 0 of the topological type of a plane or disk in R3. We'll give reference and speak in more detail, but let me just, in this overview, give you the gist of the argument. The indirect proof, joint with Brendan Guilfoyle, is as follows. If such, so it's indirect. If such a P0 existed, then its lift to TS2 would be nowhere holomorphic. So please note, we're using the term holomorphic here, not on an open sets, but at points. The Cauchy-Riemann equation or invariance under multiplication with J of the tangent space are notions that can be asked at just individual points. So if such a P0 existed, then the lift would have no holomorphic point, and therefore we can say here it would be nowhere holomorphic. Now we will show the proof now, the contradiction will arise from two main theorems. The first one is that this everywhere non-holomorphicity of the lift precludes the surface from being the boundary, the free boundary of a holomorphic disk, which is a holomorphic function of one variable into TS2, J. The proof of this item is by computing the analytic index of an associated boundary value problem for this question. For this question, how many holomorphic functions are there that map into TS2 whose boundary, holomorphic on the disk, on the unit disk, whose boundary values lie somewhere on this surface. That's a problem and an argument of global analysis and functional analysis, if you wish, and index theory will tell us there is no such under this assumption. Okay, here's a picture. We're going back. I apologize. This is now a visualization of this holomorphic curve N S sub P. So if the surface is convex, SP it is convex, so the lift to TS2 will in fact be the trace of a vector field, of a tangent vector field of S2, because the projection down to S2, which is the Gauss map, is injective. So this NSP viewed as a surface in TS2 is the trace of a vector field, or if you wish, locally, a graph. The horizontal axis here, S2, represents the base, S2, and the vertical axis, I apologize, will be the tangent space of S2. then this surface will be locally a graph in this product. The point here, NSP being a holomorphic curve, is just reflected in this graph being a holomorphic function. Since the fiber is C here in this local trivialization. And in fact, we have here, in terms of these natural coordinates, d over dz of the tangent bundle, a representation of this surface, in fact, globally as this quadratic polynomial g of z, where P1, P2, and P3 are the Euclidean coordinates of the center of the sphere when viewed in R3. Now, completion of the proof. We will show, using a heat flow with boundary condition, that in fact any surface NP in TS2 does bound a holomorphic disk with boundary in the pair TS2, comma, this sigma should be NP, so a holomorphic curve in TS2 with boundary in NP. And that will then complete the indirect proof of the Tuponoghov conjecture. Let me now go back after this bird's eye view of the what we're doing to give a little bit of more detail, slightly more detail on the methods. Now, this second existence theorem, this, if you wish, general existence theorem, relies on a metric, on LR3. The first one before did not. And in fact, the statement of the theorem, of the conjecture did not. It just spoke about umbilic points, which just need the complex structure to be described. Now we need an extra item for the existence theorem, as you can imagine, for the heat flow, because that will be a metric item. And here's the metric. Given two oriented geodesics in R3, consider pi L1 and pi L2, which are the unit direction vectors of those geodesics, and consider the vector d in R3, which is the distance vector from the line L1 to the line L2 in R3. So that is the unique vector, well, or yeah, save there, skew, that is perpendicular to both. Denote now by the distance between these two points of LR3, the signed angular momentum in R3 of the oriented line L2 about the oriented line L1. So here you have it. It is given by the Euclidean norm of the distance, of the minimal distance, d, times sine theta, where the signed angle theta is that between the two directions in the plane spanned by these two direction vectors and oriented by the normal d. Now, of course, d could be 0, but then this item would be 0 anyway. So this is a function of two variables on LR3. It's a distance function, and it's physically well motivated, and of course derives from the Euclidean metric. Here's an example. let L1 and L2 be 2 points on this normal congruence of the round sphere. Then their distance is 0, and NSP is null and holomorphic. Here you have it. Here's the line on top, L1, on bottom, and on top, L2. They are skew. D is the mutually orthogonal distance vector. We have the angle theta in this plane that I indicated, and then the distance is norm d times sine theta. It's a well-known expression in mechanics. And our situation here, if these two lines cross, then the distance vector is 0. One does not rotate about the other in this situation, and the distance is 0. Of course, there's another situation where two lines have 0 distance. That is when they are parallel. We'll speak more about this metric, but just now speak about the existence theorem. So this distance function, in fact, derives from a metric, capital G, on TS2, from a non-degenerate quadratic form, which gives rise to a signed area functional. Signed because, as we saw, there can be zeros. In fact, there can also be negative directions. So the area of a two-dimensional submanifold can have any sign. So we have here this functional cal A of sigma defined by the integral over the determinant of G over sigma, and the L2 gradient flow for this functional being given by d over dt of this sigma t equals to gradient f at that point, will shown to converge for suitable initial and boundary condition to a maximal space-like curve with boundary, and that will be shown to be holomorphic. So here's the picture. The argument takes place in TS2. The horizontal line on the bottom is the everywhere non-holomorphic normal congruence of a surface P. We will start with an initial sigma 0, that is space-like, and then increase the area by this gradient flow, retaining the boundary on that free boundary on that surface NP0, so as to and show convergence, which will be have vanishing mean curvature and be shown to be holomorphic. Here are now the references. The English version of the first appearance of the Toponogov conjecture is in 1995, Siberian Mathematical Journal. The Russian version was in 1994. Now, we are using joint work that is published here in 2004, where we analyze this lift of surfaces in R3 to surfaces in TS2. The second paper gives this metric that I spoke about and gives its differential geometry. It will be an indefinite Kähler metric, in fact, on this space TS2. This paper in 2020 is in regard to the non-existence. So that will be about this functional analytic and argument of global analysis about the index of this boundary value problem being negative, and then non-existence of holomorphic curves with prescribed boundary, which will be an outcome of what one calls regularity, namely surjectivity of the corresponding operator. So that's Freitom regularity, that is proved here. And in the second part of the proof for mean curvature flow, we have here in 2019 a convergence for this higher codimensional mean curvature flow of compact space-like submanifolds. The proof where that puts all of this together is on the archive from 2020. Now again, more formally. Let capital P in R3 be a twice differentiable complete convex surface that is homeomorphic to a plane. And we will in fact consider not an individual one, but the collection of all of such. And this collection can be given a topology. So that'll be a topological space. The conjecture of Toponogov is that for any such surface P in the collection Cal P, we have that the infimum over all points of P of the norm of the difference of kappa 1 of P minus kappa 2 of P is 0, where kappa 1 and kappa 2 are the principal curvatures. Now, we did give the conjecture earlier in a slightly, in a non-rigorous form, and there's an extra element that we didn't mention here, and we would like to get to that. Namely, we're saying here not vanishing of the difference between the principal curvatures, but we're speaking about infimum of the difference. And that is, in fact, important. And that was sort of clearly recognized by Toponogov that one has to consider this quantity. Namely, the claim of the Toponogov conjecture that this infimum of the difference is 0 implies that either or both of these, this infimum is a minimum, so that there either exists a point P, which is umbilic, for which the principal curvatures coincide, or there exists a sequence of points of P that converge to infinity in the relative topology on P, which is equivalent by properness to converging to infinity in R3, for which the difference of the principal curvatures converges to 0. The former will be called an umbilic, and the latter an umbilic at infinity. So we'll now just look at examples where one or both of these occur. And then, in fact, an interesting construction of Toponogov, an example, in which which then convinced him of his conjecture, which led him to formulate his conjecture. So once again, here, any convex complete plane in R3 has at least one umbilic, be it finite or infinite. Here are examples. Here is the standard elliptic paraboloid. Say if B is greater than 1, the set of points satisfying Z equals x squared plus by squared. Say normalized by 1/2. Now this surface is well known to have two umbilics, and we give their coordinates. Notice that b bigger than 1 here, they lie on the axis of the stronger, of the larger principal curvature of this paraboloid. However, equally, for any sequence of points P on this surface, P sub B, rather than this is a misprint, going to infinity, both principal curvatures go to 0. In fact, they go to 0 with the speed of 1 over norm P, both curvatures. So in particular, this surface also has what we would say an umbilic at infinity, namely a flat umbilic. Here you go. Okay, first, the upper picture here is a visualization of Toponogov conjecture. So on such a complete convex surface of plane type P, we have either the finite umbilic indicated by the point on the left, lower, or the sequence of points going out to infinity for which the difference goes to 0. And here is a graph of the elliptic paraboloid with its two umbilics indicated over the y-axis for b larger than 1. Now, can we get rid of the infinite umbilic? Well, first of all, we can join those two umbilics by setting b equal to 1. Here we now have a rotationally elliptic paraboloid, which has, if you wish, quote unquote, a double umbilic at the origin, and it has one infinite umbilic, the infinite umbilic. Now, can we shift the infinite umbilic? Can we get rid of that? Well, here you go. A single finite umbilic surface can be obtained from the previous example by multiplying this quadratic function by something that goes to infinity on the unit disk. So we're looking here at exponential to the power 1 minus x squared minus y squared inverse, which goes to infinity as we reach the boundary of the unit disk. And then the infimum is the minimum. We still have an umbilic point at the origin, but as we go out to infinity, one of the principal curvatures will be 1, which is the curvature of the unit circle, and the other one will be 0. So this has no infinite umbilic. Okay, so this is like the walls here become vertical rather than spreading open. Now here's the example. Now this is interesting. This is the Toponogov surface, let me call it that. So Toponogov tried to construct a counterexample. So what he did is say he considered here this situation of two umbilics, x squared plus by squared. And then he bent this surface up by that factor, which is now a graph over this ellipsoid, over this ellipse, the interior of an ellipse. And then what
I'm sorry, Wilhelm, does it should be y squared in the...
Yes. By squared. Thank you. Yes, thank you. I'm sorry, thank you. So this has two umbilics at these points, near those points that we indicated earlier, and has no infinite umbilic. And now what he did is he tried to shift these two out to infinity by letting b become large. So he gave a limit, which needs to be properly defined, of b going to infinity of this surface P of b. And that will give a surface with one infinite umbilic point and no finite umbilic point. So here's this P of b, and now he lets b go large. Of course, then the domain of these of this switches, so he has to consider some cutoff functions and so on. He didn't give details, but he said he knows it, but it's clear the construction of this type, and then shifting these to infinity, but that will create an umbilic at infinity, which did not exist for finite b's. So then he said, well, we can't shift this, so clearly it must exist. And, well, we conjectured it would exist. Here we prove the following, if you wish, slightly weaker version of the conjecture, namely, in the case of a slightly higher smoothness of C3, alpha in this class of proper convex planes, the Toponogov conjecture does hold. Again, the proof is indirect, as we indicated, and based. Now, let me give you a slightly different angle on this. Namely, if P0 is umbilic free, and we have a second surface, which is also C3 alpha smooth, that is parallel to P0, then most certainly P is also umbilic free. So the equivalence class of all smooth P0 parallel surfaces, which is encoded by this collection of normals, because the normals are common to all parallel surfaces, and the umbilicity of this, any element of this equivalence class, is reflected by holomorphicity of this equivalence class encoded by NP2 in terms of this natural complex structure in the beginning. So now, sort of the moral of the proof is that the global function theory of one complex variable is sufficiently sensitive to rule out non-umbilic complete convex surfaces, and for analytic reasons of heat flow, prove this conjecture under the stronger assumption of C3 alpha smoothness. So let's go back again. We have here our oriented geodesic. We have the direction vector pi of L and the distance to the origin vector v, which is the argument that the variable, it's the point where the function norm w takes the minimum for all vectors v that lie on this line in R3. So it's the minimum distance, and that will be in fact perpendicular to pi of L, therefore is a point in the tangent space of S2 at the point pi of L, giving rise to this bijective map L to the point of TS2. So here you go. Here's your geodesic. V is the distance vector to the origin. Pi is the direction. Then pi of L comma V is a point in the total space. It's a tangent vector of TS2. So those are diffeomorphic. And here you go. Here's now another description of the complex structure that we motivated before by rotation. Namely, consider the conformal structure small j of S2, then the complex structure capital J on the tangent bundle is just the 1,0 part of the complexification of that real bundle TS2. And this definition here, in fact, encodes this rotation that we said earlier in line space. So again, given our surface, we consider the normal congruence of those lines intersecting P that are normal. P being convex, the map pi is injective, and this NP for convex P's is a section, is a vector field of this TS2. Now here's the problem for holomorphic functions. In fact, it goes back to Riemann-Hilbert. Namely, we say the Riemann-Hilbert problem in the pair TS2, comma NP. This is a surface, a submanifold, a two-dimensional submanifold of codimension 2. Is the problem find a holomorphic map on the unit disk D and C, which maps into TS2, takes the boundary into NP. Holomorphicity here is the first star, namely the requirement that the D bar of F being defined as by just the Cauchy-Riemann equation, dF composed with J equals capital J times dF, so that this vector, this tangent vector, vanishes for all points Z in D. The second requirement for this boundary value problem in complex analysis is that the boundary of this map F lies in this submanifold. So this is a free boundary value problem. So here's a picture for that. D is the unit disk in C. F is a holomorphic map into TS2, which takes boundary, whose boundary lies in this surface. So this equation star is the elliptic Cauchy-Riemann operator for F, and double star will then be an elliptic boundary condition. Here's now, very briefly, the analytic framework for this problem. Consider all smooth maps, all smooth surfaces, all smooth sections, say, all smooth boundary conditions, sigma, which are sections, all vector fields, if you wish, in TS2. Those are all boundary conditions. Consider next all C2 smooth surfaces of disk type in TS2 whose boundary lie on one of these elements sigma of the boundary conditions. Now we define a submanifold of the product of these two Banach manifolds called H. Well, that is simply the collection of pairs of smooth maps and boundary conditions such that F is a solution of the Riemann-Hilbert problem with that very boundary condition. H for holomorphic. Now consider the projection of this collection of holomorphic surfaces to its boundary value. So that is capital pi. So then pi is a nonlinear Freitalm operator of Banach manifolds, which is saying that the linearization of this projection at a point, at a pair of holomorphic disk and boundary condition has a finite dimensional kernel, has finite dimensional co-kernel, and closed range. So this is just a reflection of, okay, let me first give the picture here. H, this line on top, is the collection of all holomorphic disks with boundary on all surfaces sigma. We project them to the very surface sigma on which on which the boundary lies. That's capital pi. Then the kernel of this, of the linearization at one point, is just the tangent space of that that holomorphic of that variety, and the dimension of that kernel is the dimension of that variety on top. The index of this map at a point, comma sigma, is the dimension of the kernel minus the dimension of the co-kernel. The Riemann-Roch theorem tells us that this index is the Maslov, which is, it's a finite number because of those, both of those are finite, are integers, because it's Freitalm. And now the index of that operator by Riemann-Roch is just this Maslov winding number of the boundary of this F in this totally real surface, sigma plus 2. Namely, it's the winding number of a loop in this trivialized SP 4 over O4, over O2. This should be O2, which has infinite fundamental group. Now, the regularity theorem that published in 2020 says the following. Let P0 be umbilic free, which is saying that the infimum, including at infinity, so that's required, so that the infimum of this difference is greater than 0. And assume that we have a holomorphic curve with that boundary value. Then there exists a dense open subset of a neighborhood of that image point NP0 of capital pi, such that for all points of that dense open neighborhood, we have that the co-kernel of the linearization of the map vanishes. So this is called regularity. Vanishing of co-kernel just is, you know, that's regular. That's like a regular linear map. So now the existence theorem, let us get to that, is that given such an umbilic free surface, there does exist a solution of the Riemann-Hilbert problem. So given those two, let me just run you through the proof, slightly more detail of the topological conjecture. Assume here that the infimum of the difference is greater than 0 of the principal curvatures. Then there exists no finite or infinite umbilic point on NP0. So this surface is totally real. A perturbation of this surface will then also be totally real and will be a regular value by the regularity theorem of pi. Sigma being simply connected, the Maslov index of any loop vanishes, By existence and regularity, we have for a regular value of sigma that the index now is equal to the co-kernel, because the kernel vanishes, because the co-kernel vanishes. Now by Riemann-Roch, the index is 2 because of the vanishing of the Maslov index, which gives that the dimension of the kernel of pi is 2. However, the dimension of the reparametrization group of the disk is 3, the Möbius transformation maps of the unit disk. So the virtual dimension of the space of unparametrized disks is 2 minus 3, which is minus 1. Now, negative dimension of kernel tells you that there is no kernel. There is no solution of Riemann-Hilbert problem, which contradicts the existence. So that is an outline of the proof. Let me just, maybe I should stop pretty soon. So it's this metric that is key to the existence theorem, and it is defined, as we said, as it derives from this angular momentum, but in fact it can be it's the pullback of the canonical symplectic form on the cotangent bundle of TS2 via the round metric, and then entering the J will give rise, can be shown, that's what we show in our paper, to this metric G, distance is D. And so this manifold has signature 2,2, it is scalar, and one can sort of, in local coordinates, work out this fact, that the scalar manifold. Later, we, after working out here this, apologize, it's much too long. Here's this curvature flow. Let me just stop with that. Here's the problem, the problem for this curvature flow. We're looking at a family of maps of D into TS2 that flows by the mean curvature. And here's the boundary conditions, namely, we start with an initial surface. The boundary lies on that normal congruence of P0, and the hyperbolic angle is required to be constant. And finally, we can also, there'll be three boundary conditions, excuse me, we require asymptotic holomorphicity of this at the boundary. So this can be shown to be an elliptic boundary value problem. We can extract correct estimates for C0, C1, C2 estimates for this, and extract by this forcing on the boundary, a holomorphic subsequent limit for the solution of this flow. So let me stop here, and thank you very much.
Thank you, Finn. Now we need to manage questions. So let's begin with questions from the internet. Please, our remote users, remember to unmute your microphone before.
Excuse me, can I ask?
Yes.
Does the subject relates to the Carateodori problem?
Not directly. It is a similar sort of statement. Indeed, the Carateodori problem also is about existence of umbilic points. However, That is on a compact surface in the case of Carathéodory. Here, this is on a proper open surface. So it is not the case that one implies the other.
Is my understanding right that Toponogov first started the Carathéodory problem? And
I don't
then
know.
he moved to this kind of
That's a good question. He doesn't say that. I don't know. It may be. I have no idea. Somebody of you may know this better. He doesn't. Well, he doesn't give it away in his paper. Certainly, none of the methods that of the proof and so on would apply of the arguments in his paper. You see, it's a different situation. However, he may have been sort of initially motivated by it, certainly not by the methods. The methods have led him, the situation has led him to very different methods, and he did prove this conjecture, I should have said that, under an additional assumption on the proper surface P. Namely, if the mean, he proved that if the mean curvature of the surface is bounded at infinity. Then he said, yes, there must exist an either finite or infinite umbilic. And yes, so it's interesting. Yes. And the proof of that did use sort of spheres and parallel families of spheres that he rolled around in the surface. And that is sort of reminiscent, of course, on what we do, because we consider the lines that go through the centers of those spheres. So it's very interesting that he sort of he had some sense of these methods that we, of course, sort of take into this other space, and we use complex analysis and the curvature flow.
Okay, thank you.
Thank you.
Other questions from
I'm sorry, Professor Klingenberg, at the very beginning of your talk, you have represented graph of the function g as ns sub p. So is this surface, does this surface has any singularity, or it is just regular at
No, you see, so it's a quadratic. It's in TS2. Yes, you're asking. TS2. No, answer no, because we only did this on a patch. You see, on a Euclidean patch on C on a C patch. This surface is in fact not. It looks like it because it's a quadratic function, but that's just due to the choice of this C coordinate on the complement of a point of the sphere. No, this is a holomorphic quadratic sort of rational curve in TS. Yes.
Thank you.
You're welcome. Well, thank you very much again. Thank you for coming, and thank the organizers in particular for putting on this conference.
Okay, maybe someone in the room have further questions.
Yes.
Yeah. Do you see the room? Well, we don't see, but anyway, I see. Well, it seems that no, and well, we have a coffee break now here, but maybe Professor Klingenberg can go to breakout room 1 and may wait for someone who might to discuss, well, might want to discuss details of this wonderful result.
Can you tell me breakout room 1?
Well, can you move there yourself? I can try to send.
Layer 1.
Really movable. So you don't need assistance of organizers to move them. Is it? No, it doesn't work.
It should. No, it should.
No, I can send you there. Then, okay?
Please, can you send this address to other participants?
It is not an address. See, in your Zoom interface,
Zoom interface, yeah.
you in the bottom you have this breakout rooms button.
Ah, breakout rooms. Yes.
Breakout
It's the
room,
more.
yes.
It's the button more. ...
Oh, yeah, yeah. If your screen is too narrow, it can be under more. Yeah. And when you open that, you see all our 10 breakout rooms, and two of them are actually connected to physical rooms, and people here can find it's 224 and 222 probably. Yeah.
I'm sorry, in Russian this is «Войти в сессионный зал».
Yes, I believe so.
Thank you. Mhm.
You can move freely between them. That's the point. It's not as easy as if you could maybe be walking around the institute here, but it's some approximation. You can just push enter or join or whatever, and then you can leave breakout room and so on. So we have Так, а как тут это делается? Instance?
Там сейчас надо было смотреть, то есть там чат был, какое-то сообщение было в чате.
В чате было сообщение, что кто-то просил всех
это
заткнуться.
Просто
Но
я потому что не только сказать, что
в следующий раз мы
Вот фильм можно собрать. Все, что с этого зала.
Да, теперь, по идее, у нас звук сейчас
С маленьким микрофоном.
Давайте спросим нового участника.
Куда? На клавиш?
Вот это, наверное, для... Так, как слышно? Слышно ли в зуме? Есть ли звук в зуме? Кто-нибудь может что-нибудь сказать в зуме?
Да, слышно вас. Хорошо слышно.
Слышно, да, хорошо?
Да.
Хорошо.
Отлично. Карточка. Да, скажите, дайте.
Наверное, да. Ага. Как раз все включили для очного доклада. Сейчас народ соберется. О, даже название набрали.
Да.
Отлично. Просто красота. В принципе, объявляющий, может быть, не, ну, наверное, нужен для приличия. Да, наверное, надо. Сейчас, как мы... Видим ли мы участников?
Скажите им, чтобы они пришли.
Dear participants, we're waiting for the beginning of the next talk, but please mute your microphones on the time during the talk. Убрать это все. Ну что, народ?
Sorry, can we ask questions during the talk?
Yes. If you want to ask questions, you just unmute it temporarily and mute it back because, well, there are always background noises around any computer. Like if everyone unmutes microphones, we will hear a lot of extra noises. So let us begin the next talk. And the speaker is Nina Lebedeva from Steklov Institute at St. Petersburg, and she will speak about locally homogeneous C0 manifolds, Riemannian manifolds.
Let me thank organizers for opportunity to give this talk. My talk about joint work.
Oops.
with Artyom Dmitrий, and it is about C0 homogeneous Riemannian manifolds. Let me start with some definition and formulation of main theorem. So let X be a metric space. We say that X is locally homogeneous. Or sometimes it is called weakly locally homogeneous. If for any points in X there exists small number such that there exists isometry between a metric ball around X to the metric ball with radius R around Y, and such that f of X equals Y. So in each point, R would be different, so arbitrarily small. And so let me say how we use the notion of C0 Riemannian manifold. It is C1 smooth manifold. This C0 metric tensor. So our main theorem is the following: let X be C0 Riemannian manifold, then in fact X is smooth Riemannian manifold. So let me say something where this question comes from and what could be asked in this direction.
Can I ask, do you mean X is locally homogeneous?
Yeah, oh, I'm sorry. I'm sorry. Yeah. X is locally homogeneous. Oh. So let X again be arbitrary metric space.
May I ask? This is a local. It's a local result. Yes.
Is it a local result?
Yeah, it's local result. Absolutely.
Yes.
Local result. Actually, we can come to a neighborhood of any point and do everything there.
Yes. Thank you. Thank you. Very nice.
Complete, right?
Yeah. So suppose some group acts on metric space by isometries, or maybe not a group, but some group-like object, for example, pseudo group or local group. acts on X or acts locally on X by isometries or by local isometries. Then what we could ask, if we know something about X, for example, X is C0 manifold, or maybe Alexandrov space, or maybe some other constraints on geometry of metric space X, then we could say something about a group G that could act by isometry on X. And secondly, suppose G acts transitively on X. This means for any X and Y, there exists element in G that takes X to Y. Then, under some additional assumption, we could say that X may be homeomorphic to coset space of G by isotropic group or group like object. So here is very informal statement. So in different cases, this quotient somehow could be defined. Actually, G not necessarily a group, and H is not necessarily subgroup. So in this case, we can, if we know initially something about X, then we can say something about G, and then we can say again something about X, because X could be obtained this way from G. And actually, it could be useful because there is a structured theory for locally compact group, namely fifth Hilbert problem, which I will formulate a little bit later. So we can say something about G, maybe that it is a Lie group, and then we can say something about X, for example, that it is smooth. So let me mention some results. Previous, let me remind firstly the famous Myers-Steinrod theorem. Proved in 39. If M is smooth Riemannian manifold, then isometry group of M is a Lie group. And actually, this theorem also could be proved via fifth Hilbert problem that was proved actually later. It's known that Gleason-Yamabe theorem let G be a topological group and there are different formulations of this problem. One of it states that G is locally Euclidean. Then G is any group. But this condition sometimes is not easy to verify, and there's another formulation and actually different statement. If G is locally compact, and G has no small subgroups. No small subgroup means that there exists a neighborhood of identity element such that there is no subgroup of G in this neighborhood of identity. So, and conclusion is the same, that G is a Lie group. So actually, the main difficulty in our case is that we don't have that our isometries form a group, and actually Hilbert problem was proved sufficiently recently by Goldring in 2010 for local group. Local groups. But again, we have difficulty here because local isometries do not form a local group. So I didn't remind the definition, but the notion of local group can be defined via some properties, like a group with partially defined operations. But one can think that this is just neighborhood of the identity in some group. So, but actually our isometries don't form a local group, but form only pseudo group. And the main technical ingredient of the proof is to make a local, is to show that this pseudo group is in fact a group. And actually, main geometric ingredient is the following. We can find some fixed positive number such that any isometry from the definition of locally homogeneous space with arbitrary small radius r could be extended to the isometry of a ball with fixed radius to all points. And actually, it is not difficult to prove then that these isometries will form a local group, not just pseudo group. So let me mention some previous results. Firstly, for non-local case, and when initial formulation of Hilbert problem could be applied. In 94, Fukaya Imaguchi proved that for Alexandrov space, which is homogeneous, not just locally homogeneous, isometry group is a Lie group. So then, quite recently, the same was proved for much more general spaces as Alexandrov spaces, namely for RCD spaces, that is spaces with Ricci curvature bounded below, with some definition, synthetic definition for boundedness of Ricci curvature. It was proved by Guiara, Santa Rodriguez. So the conclusion is the same, that isometry group of such a space is a Lie group. I'm sorry, there should be no this condition of homogeneity in this theorem. Just isometry group of Alexandrov space. And let me mention also result of Berestovsky. he showed that under some sufficiently mild assumption on metric space X, such as existence of some angles, for example, Alexandrov space. For Alexandrov space, the theorem work, he proves that if X is homogeneous, then X is isometric to a smooth homogeneous space, Riemannian manifold. But all this result is for spaces where we have a group action. So, and let me mention some local results where where you have no group action, but action of pseudo group. So we were asked this question by Christoph Böhm, and in their paper authors proved some very particular case of this theorem. They had some limit in the Ricci flow. Then Francesco Pediconi wrote different papers with different additional assumption on the smoothness of manifold or metric space, and obtained the same result for locally homogeneous spaces, but with some additional restrictive assumption. Actually, I would like to stop here. Thank you for your attention.
So we have 10 minutes for questions. Are there any questions from the internet? First, please don't forget to unmute your microphone before asking. Well, there were some questions during the talk. Any questions from the room here?
Yes. May I ask a reporter?
Could you repeat your question?
My question about Berestovsky theorem. About Berestovsky theorem. As a homogeneous space or locally
Yeah,
homogeneous space?
Globally homogeneous.
Globally. Okay. Thank you.
Please recall what difference between classical group and pseudo.
Okay, I wouldn't like to about exact definition, but this pseudo group comes from if
Nina, could you please repeat the question, because we have all the microphone is only on you.
What is the difference between classical group and pseudo group? Yeah, I don't want to give a definition, but pseudo group, if you have something that acts on manifold by homeomorphism locally, you write these properties and you obtain a pseudo group. Extract the properties from this action locally defined on neighborhoods, on open sets. And local group, it also could be defined axiomatically. It's like a group, but with partially defined operation around the identity. You can multiply only elements around the identity. Yeah, and you can think about local group like about a neighborhood of the unit element in a group, in an ordinary group.
Can you provide some examples of pseudo groups?
That are not local groups, probably.
I don't know what.
So what is missing? Associativity or what?
Actually, if you take homeomorphism, I think it will be not a local group.
Maybe circle in R2.
Not unique inverse element. Yeah, sensitivity, I think, will be missed.
No composition rule, something different instead of binary operation. Well, what is it? Could you give an idea what is the difference of definitions? Like everyone understands that if you restrict to a neighborhood of identity, you get partially defined product, right? And you just say that all identities in the definition of group are satisfied in smaller neighborhoods. That's easy to construct. What kind of property should you like to give a definition? I don't know what is a pseudo group, Nina. Honestly.
It's just local group.
Yeah, what I said is a local group. Yes.
Yeah,
what is a pseudo group? What type of properties one looks at in the definition?
It is not pseudo group. It's just local.
No. Local group is much stronger conditions than pseudo.
Yeah. Pseudo group is some very large class,
very
right?
Mild, yeah.
Or a priori, at least. What is this? Is it a set with some binary operation, or it's something complicated?
Can you provide an example? Group is no classical group, but is pseudo group in neighborhood of some
Sorry.
Example of a pseudo group that is not a local group or whatever. The group of part of local homeomorphisms.
Yeah.
So the elements are kind of homeomorphism of, say, from one open set of subset of plane to another, right?
Yeah.
What is separation in homomorphism?
Composition, yeah.
Which is sometimes undefined because the domain and range do not intersect, something like this.
Yeah.
Unit element is indeed.
There is no unit element. Okay, yeah, maybe this is big different. Some problems with unit element in pseudo group.
Oh, but so the global identity is not included? Or sufficiently small, maybe? Well, something like that, yeah.
Too much question.
Probably we got an idea. Yeah, we have 5 more minutes for questions.
I have a question.
Yeah.
So in the theorem of Fukaya Yamaguchi,
Yeah.
is there an assumption on lower? Is there a lower curvature bound that is required?
Yeah, by Alexandrov space, I mean spaces with curvature bounded from below.
I see. Yes. Yes. So and the method of in this paper on RCD, do they also do this collapsing methods?
Sorry. In Fukaya Yamaguchi, there is no RCD spaces.
Yes, in the next paper.
Yeah, in RCD, you asked what is method?
They also use similar method as Fukaya?
Yeah, it's again Fives-Gilbert conjecture, and they prove that there is no small subgroups. By contradiction, they assume that there are small subgroup, and they obtain the condition of Fives-Gilbert problems that there is no small subgroups there.
I see.
Group.
Interesting. Thank you.
But it's a global isometry group, right?
Global.
Nothing of that local stuff.
Yeah.
And do you know anything about local analogs of this, like, well, something that where you can plug in a non-complete neighborhood of a point in Euclidean plane, like, right?
Mm-hmm.
Do you know something like this for Alexander spaces or RCD?
Sorry, could you?
I mean, local result is some kind of local isometry group in this.
Actually,
something like yours, right? But for Alexander.
Actually, Alexandrov space, if it is homogeneous, then it is C0 remaining manifold because around Euclidean point there is a smooth chart, C1 chart.
So not just Lipschitz, but C0. I see. That's C0. Okay. So this applies to Alexander spaces.
Yeah.
Okay. Any other questions? So, if there are none, let's thank the speaker again. For organizational issues, we have a. Oh no, we have no organizational issue. We have the next talk in 10 minutes. Eight minutes. Так, следующий доклад, он будет со слайдами. Вот это мы убираем сейчас, да? Сейчас мы сделаем. А будут чистые слайды, доски не надо. Так, как бы тут выйти? Ага. Сейчас. Листалка слайдов. Во-первых, надо проектор включить, во-вторых, звук. Сейчас делаем. Можно сидя, если ничего. Можно вот здесь за этим компьютером. Ну, сейчас, да, может быть. Сейчас я найду самые слайды. Да. Так, Ctrl-L. Так, вот это слайды. Сейчас. Нет, тут есть у нас листалка.
Только вы следите, если слайд не сменится.
Хорошо, да. Так, его надо включить для начала. Я листалку. Она включена. Да. Вот, значит, листалка. Можно стол поставить? Не. Это наша. А где у нее? О, представь. Можно не всегда, можно сесть за компьютер и жать пробел. Чем, да, на очень. Давайте, да, просто за компьютер, а стрелки здесь.
То есть на компьютере с клавиатурой.
Ну, можно, если это удобнее, чем так. Да, вот он здесь сбоком, этот стул.
То есть и как?
Ага, опа.
Это я. Вот смотрите, вот стрелка влево, вот стрелка вправо. Все, да? Вот он листает.
Да, это
Ну, все,
две стрелки.
Вот он листает сейчас, да?
Да, а вам надо как-то сообщать, что там на экране?
Нет, я помню наизусть.
Ну, если лишняя промотка.
Мне главное, вот я стрелку могу нажать, а он не сработает.
Вот сейчас на первое.
Все, я понял. Так,
головочный.
теперь, то есть вот мне прям так сидеть. Вы меня не видно будете.
Ну, хороший вопрос. Да, видно затылка, но я думаю... Кстати, она же беспроводная. Давайте попробуем. Куда угодно она идет. Где можно сидеть? О, вот так. Колени пойдут, хотя бы... Как на пианино. Какие варианты? Можно столом, но здесь нет ни одного стола. Здесь все хорошо, но все, на столы все тут загружены. Микрофон здесь надо его куда-то в него как карман положить, чтобы он, да, чтобы не сесть на него случайно.
Все, я готов.
Ага, ну еще, в принципе, 5 минут. Беремся. Наверное, уже пора.
Я вот забыл коронку, к сожалению. Я думаю, что-то я все-таки забыл. Хотел коронку, чтобы лучше слышно. Плохо слышно? Или нормально?
Ну, в принципе, надо минус спросить. Было слышно? Не было слышно. В принципе, нормально. Ну, это туда ушел, а именно как-то туда прислушивался. Все равно нужно было прислушиваться.
Ну, я завтра я...
Уместно нет, неужели тут такие залы пришли?
Ну, можно...
Правда, тут даже все эти залы показывают. Так, сейчас звоним начало. Сейчас что у нас идет? Звук идет?
Ну, пока нет. Вот эти
два микрофона. Слушали еще минуту? Да, можно, собственно, не тянуть со временем. Так, а у меня вот этот микрофон тоже работает. So, let's begin our next talk. Will be by Evgeny Korny from Kemerovo, and the title is almost paracomplex structures on six-dimensional sphere. So please.
Okay. Actually, I second time in this institute. The first time I was here 7 years ago and told about classic, almost complex structure. And now I will talk about paracomplex structure. And first, some words about what is the difference between paracomplex structures and almost classical complex structures. Paracomplex structure, almost paracomplex structure is antipode of almost complex structures. And it is well-known fact that even dimensional sphere S2 admits complex structure, four-dimensional sphere nor admit complex structures, six-dimensional sphere admit almost complex structure, but is open questions exist on six-dimensional sphere integrable almost complex structure, by other word, admit as six-dimensional sphere and complex structures. It is open questions. And for all even dimensional sphere from dimensional 8 and above, it is topological known fact that all this sphere no admit almost complex structures and actually complex structures. By this way, only AS2, it is two-dimensional sphere, and six-dimensional sphere admit almost complex structures, but paracomplex structures is antipode of almost complex structures. And next questions, what about even dimensional sphere if we consider almost paracomplex structures? For two-dimensional sphere, it is a well-known fact that two-dimensional sphere no admits paracomplex structure. Paracomplex structure is just tangent spaces automorphism continuous field that is squared is entity operator field. Okay, now I start my presentation. If I have a first slide, the title slide. First slide. Okay, title first. Okay, we have seven-dimensional Euclidean space, classical R7, and we have cross-product operation. By other words, we can consider our seven-dimensional Euclidean space as a space of imaginary octonions. It is well known identify operation. If we have a point of seven Euclidean space, this point is ordered set of seven real numbers, x1 and so on, and x7. And we just take this set of real seven numbers as coefficients of imaginary octonion. We just have an octonion who has coefficients x1 and so on, x7. This is simply identification, real seven-dimensional Euclidean space and imaginary octonion space. By this way, we have a cross-product operation. It is generalization of cross-product operation in three-dimensional Euclidean space. Here we have a seven-dimensional space, and operation B looks like a two form, B of Q1, Q2, and we define this form as B of Q1, Q2 is imaginary part of multiplication Q1 and Q2. Q1 is imaginary octanion and Q2 is imaginary octanion, and we have a result of this operation. B of Q1, Q2 is some octanion, and we call that this octanion is a cross product of Q1 and Q2. We can define the standard inner product in our 7-dimensional Euclidean space as real part of multiplication Q1 and Q2 bar. Q2 bar denotes their octanion conjugation. By other words, Q1 bar just minus Q2. Sorry, Q2 bar is minus Q2. It's classical conjugation of octanion. Now we have a G2 group. What is G2 group? G2 group is a Lie group that consists of orthogonal symmetries of, with respect to cross product operation above, that's defined above. By other word, G2 consists of orthogonal linear transformation K, and K commutates with B. G2 is simply 14-dimensional compact Lie group. We consider 6-dimensional sphere denoted by S6 as a homogeneous space G2 divided by SU3. SU3 is standard special unitary group that consists of complex Hermitian transformation of 3-dimensional complex space. Okay, is next slide. Yes.
Definition 1.
Definition 1. Okay. Right. Now we have a definition, strict definition of almost paracomplex structure. Let M be a 2n-dimensional manifold. N is a real number. It is necessary condition that M has two-dimensional, real two-dimensional. Let M be 2n-dimensional manifold, and almost paracomplex structure on M is continuous tangent subspaces automorphism field P, and P squared is just identify operators field, but denoted by ID. If M is homogeneous space, G divided by H is isotropic group, it's a classical notion. M is G divided by H, when it is said to be P is G invariant almost paracomplex structure if for each element G in capital G, we have DG commutates with P, where DG is a derivative of map G. G as a map from M to M, and we have linear map DG that acts on tangent bundle. If we have almost paracomplex structure P on 2n-dimensional manifold M, each almost paracomplex structures defines two tangent subspaces distribution D plus and D minus, so that P restricted to D plus is just identify operator field, and P restricted to D minus is just minus ID operator field, because each almost para-complex structures have only two eigenvalues, plus 1 and minus 1. Because P squared is minus identify operator, it follows that P has only two eigenvalue separators, plus minus 1, and just D plus its distribution that corresponds to eigenvalues 1, and D minus is distribution corresponds to corresponding to minus 1 eigenvalue. Conversely, if we have pair of two distribution of rank n, if m is dimensional 2n, and tangent bundle is a Whitney sum of this distribution, D plus and D minus, this pair of distribution defines an almost para-complex structures up to multiplying by minus 1. We just take D plus and D minus as eigen distribution for this almost para-complex structure. By the word, each pair of tangent spaces distributions of the same rank defines up to multiplying by minus y the same almost para-complex structure. It is said that almost para-complex structures is integrable, to be integrable, if this distribution D plus and D minus is involutive with respect to Lie bracket operation for vector fields on M, vector fields Lie bracket operation on M. And almost para-complex structures is called integrable almost para-complex structures if D plus and D minus is involutive, and integrable almost para-complex structures is called para-complex structures. It is totally similar to, absolutely similar to classic almost complex structures. Next slide. Okay, next slide.
Definition 2 now.
Okay, let M be two n-dimensional manifold, n-dimensional manifold, and omega be linear skew symmetric form on M, and we have the next definition. Radical omega radical at the point x in M, it is vector subspace, so that each vector from this subspace denoted by red omega x, it is point in the M, so that for which vector v in red omega x we have that interior product v and omega x form is 0. Here I v denotes the linear form, so that this form is omega, so that the first argument is just v. By other word, we replace the first argument in v with a particular vector v. This radical, sometimes called a kernel of omega, I use definition as a radical. Okay, radical of omega form is so vector subspace. So for every vector v, we have just interior product v and omega is 0. But is radical in a particular point x, but we now define total radical omega radical on manifold M. Radical omega on manifold M is just union of red omega x over all point P in manifold M, as you see here. Actually, this distribution may be different rank in each point. And now we have a definition. What is regular skew symmetric form? Skew symmetric form omega is called regular if red omega has a constant rank over M. By other word, if omega has the constant rank in each point in M. If M is homogeneous space G divided by H, it is said that omega G is G invariant linear form to be invariant G invariant form if for each element G dG provides omega form. If omega is G invariant skew symmetric P form with radical of rank n on manifold M, I recall that manifold M must have rank 2n. Then omega radical, it is just G invariant distribution of rank n on manifold M. If manifold M admits G invariant Riemannian metric, and we have orthogonal complement to radical omega, and we have that this orthogonal complement also has radical n, and tangent space is just Whitney sum of this distribution. The first distribution is omega radical, which had rank n, and the second distribution is its orthogonal complement with respect some G invariant metric. And this follows that we have pair of two G invariant distribution of the same rank n, and the Whitney sum of this distribution is tangent space, and we have that this pair of distribution defines some almost power complex structures, more strictly G invariant almost power complex structures. This almost complex structure defines by distribution omega radical and its orthogonal complement. And we have that each G invariant P form with rank of radical n defines a G invariant almost power complex structure on manifold M. What is in this slide?
Let G2 be
yes, I understand. Okay, I recall that we consider a six-dimensional sphere as 6S homogeneous space G2 divided by H. And here you see a Lie algebra of with homogeneous space. Let G be Lie algebra, G2. Yes, G2 be Lie algebra of group G2, and H be Lie group of isotropy subgroup, where H is isotropy subgroup SU3, because S6 is G2 divided by SU3 by this denotes H is isotropy subgroup. Okay, and P is orthogonal complement to isotropy subgroup H with respect some B-invariant Riemannian metric on G2. And we have that P is some vector subspace in Lie algebra G. Now consider P star. P star is dual space that consists of all left invariant one form on G2, and so that this form, those form can provide non-zero values only on P. By other words, P is non-zero set for dual space P star. Now we have three exterior degree of P stars, and we have left invariant basis: theta 1, which theta 2, which theta 3. This free form left invariant basic of this space P star in 3 degree. Yes, we have this basis, and it is clear that each left invariant basic 3 form theta I, theta j, theta k has a radical of rank 3. This radical just is intersection of kernel theta I and theta j and theta k. It is very simply refined fact. Well, now we have that all left invariant basic 3 form always has radical of rank 3. Since G2 is compact, since H is compact subgroup, it always admits a B-invariant measure mu. And now we can take integrals over H of any skew symmetric free form with measure mu. We have that each integral over H, it is G2 left invariant and H right invariant free linear free form on G2. Okay, is next slide.
Proposition 3.
Is next slide. Now we a key proposition. This proposition help us to obtain the next results. Okay, proposition. Let omega ijk is integral over H of basic free form theta I, H wedge theta J, which theta K with measure mu. Then first, omega I, first exist indexes I, J, K, so that omega I, J, K is non-zero free skew symmetric free form, and with form for this particular indexes omega ijk is G2 left invariant and H right invariant free skew symmetric form on G2 group, and this form has radical of rank 3. Rank 3. Second statement. Distribution omega radical and its orthogonal complement with respect some B invariant metric are H invariant distribution on G2 group. By other words, this distribution is invariant with respect of action of different derivative of adjoint action of H on Lie algebra H. And third statement of this proposition that distribution omega radical and its orthogonal complement are not involutive distribution with respect of Lie bracket operation. Lie bracket operation here is Lie bracket operation in the algebra of group G2. Okay. This previous proposition give us that G2 admits G2 left invariant and H right invariant free form. This free form is skew symmetric free form with radical of rank 3, and this skew symmetric form induces G2 invariant free form on homogeneous space 6 on homogeneous space S6, and we have that this free form from previous proposition induces free form omega 0. Omega 0, it is linear skew symmetric free form with radical of rank 3 on S6, and this form has radical of rank 3. As I said above, now we have that free skew symmetric form omega 0 defines the pair of definition. The pair of distribution. The first distribution is omega radical. This distribution has rank 3, and its orthogonal complement has rank 3 also. And now we have that free form omega 0 on S6 defines the pair of tangent subspaces distribution of the same rank 3, and this distribution defines their some almost power complex structure. This almost power complex structure defines by a simple way. Their eigenvalue, which corresponds to eigenvalue +1, it is radical, omega radical, and the second distribution, which corresponds to orthogonal complement to radical omega, it is distribution that correspond to eigenvalue -1, and we have that with free form omega 0 defines G2 invariant almost power complex structure on 6-dimensional sphere as 6 on 3-dimensional sphere S6. Using the fact that G2 is simply group, it can provide that distribution red omega and its orthogonal complement are not involutive distribution. As I said above, almost power complex structure is called integrable if this distribution are involutive. Because this distribution are no involutive, we have that almost power complex structure defined by free form omega 0, defined non-integrable almost power complex structure. Moreover, we can generalize this fact, and we have the next proposition. Six-dimensional sphere admits G2 invariant integrable almost power complex structure. Okay, next slide. I don't know what is here.
Proposition 5. And some formulas above that.
Oh, okay. As it is well known that for standard almost complex structures exist the concept of Nijin-Hayes tensor, and for almost power complex structure now we have Nijin-Hayes tensor analog. It is a tensor field psi, and this is tensor field psi is a tensor field so that psi of x and y is real vector fields on manifold M, and psi of x and y defined as you see here. Here we use Lie bracket of vector fields and Lie bracket of values psi on x and y. It just looks like a standard Nijin-Hayes tensor. Difference is 1 sign replaced from minus to plus. It is tensor field is similar to Nijin-Hayes tensor for almost power complex structures. Also, similar to almost complex structures, this tensor field provides criteria of integrability of almost complex structures. That is a statement in states in this proposition. The next let psi is tensor field for almost power complex structure P on manifold M of dimension 2, and then almost power complex structure P is integrable if and only if the tensor field Psi vanishes on M. It is similar as Nijin-Hayes tensor vanishes on M, but only for standard almost complex structures. It follows that tensor field Psi is non-zero tensor field on S6, because as I said above, almost complex structure defined by free skew symmetric form with radical of rank 3 is known integrability, and because this almost complex structure is known integrability, its tensor field psi is non-zero tensor field on S7. By other words, we have that S7 admits G2 invariant almost para-complex structure, but this almost para-complex structure is no integrable. Moreover, six-dimensional sphere no admits G2 invariant integrable almost para-complex structures. So this result is similar to well-known result for almost complex structures. It is well known that six-dimensional sphere admits G2 invariant non-integrable complex structure, but admits integrable G2 invariant complex structures. Okay, here last slide. Final total result. I formulate this in next statement. Theorem. This theorem is total result of my talk. What it states? Six-dimensional sphere admits G2 invariant almost para-complex structures, but no admits G2 invariant integrable almost para-complex structure. By other words, no admits G2 invariant para-complex structures. Additionally, six-dimensional sphere admits G2 invariant skew symmetric free form with radical of rank 3. With radical of rank 3, we construct this form above and use this free form. We obtain G2 invariant almost para-complex structures. By word, it is open question. Admits or no admits six-dimensional sphere non-invariant almost para-complex structures and integrable almost para-complex structures. This last statement provides a result for G2 invariant almost para-complex structures, but is I don't know where exist on six-dimensional sphere non-invariant almost para-complex structures. Moreover, integrable almost para-complex structures. If we talk about complex and almost complex structure on six-dimensional sphere, it is well-known result that six-dimensional spheres admits non-integrable almost complex structures. In this proposition, we see that six-dimensional sphere admits G2 invariant non-integrable almost para-complex structures. But this G2 invariant almost para-complex structure is non-integrable. I don't know. Can we obtain use my machinery of a degenerated free form with radical of rank 3 to construct some integrable almost para-complex structures? Just I have provided a result that if we have free skew symmetric closed free form on six-dimensional sphere, then this closed free form defines integrable almost para-complex structure. But I don't know, can I construct a closed free symmetric form on six manifold? In this talk, I just construct non-closed free skew symmetric form. This form is not closed, and this form has radical of rank 3. Maybe we can construct a free symmetric form that is closed but with no have radical of rank 3. For my for my technique, we just construct free skew-symmetric form with radical of rank 3. It is necessary a condition, but I don't know. Can we use provide this form or no? And here and see here my paper in which you can find more strictly in detail and more detail description of this result. I think I stop here. Thank you for your attention, and I'm finished.
Are there any questions? Well, the internet, from the internet, please unmute yourself if you have questions.
May I ask you?
Yeah, sure.
Evgeny, what can you say about history of this notion? I say about paracomplex structures. Some words.
What do you mean? A paracomplex structure or
yes.
Classic complex structures? Paracomplex structures or classic complex structures?
Yes, about.
If we have classic complex structures, this complex structure defined as tangent subspaces, automorphism, a continuous field. For example, denote this field by letter J. And classic almost complex structures. If tangent space automorphisms field J, so that J squared is minus identify operators field. But this field is a real field, but this real field, no real eigenvalues. It has complex eigenvalues if we take a complexification of tangent space. If we talk about paracomplex structures, the paracomplex structures is real field, and we have tangent space automorphism field, for example, P, so that P square, it is...
Excuse me, who considered paracomplex structure before you?
Complex structure?
Paracomplex structure. Where the definition
yes.
came from? Who invited the
Can you find my third slide and
yes.
see definition? Please,
third
definition.
Counting. Yes, we have definition 1. Yes, it's on the screen.
Paracomplex structure, it is field P. It is field that provides automorphism field, automorphism for real tangent spaces. This field, just P squared, is identify operator fields. By other word, P squared is plus 1 or minus. Sorry, P squared is 1. For classical complex structures, P squared is minus identified field. For paracomplex structure, P squared is plus identified field. It is difference between complex structures and paracomplex structures. I understand.
Thank you.
Oh, but by the way, why both D plus and D minus should have rank n? Is it the part of a definition or something?
No. It is just it is just a property of definition of power complex structures. But
can't you take P equals identity? Probably not. But what is the definition prevents taking just the identity?
Sorry.
Yeah, I mean the definition reads that
P squared is identified.
Identity, right?
Identity.
Can I take P equal identity?
No.
No, why not?
No. If we take P is identified, we just identify operator field. A definition of power complex structure. I think.
Well, maybe it's what is written below. It should be part of a definition.
I think you are right. The definition must be more strictly.
Yeah. What is written below the square definition? It should be included in definition.
I think this definition is not correct formulated.
Yeah. The two subspace, the two distributions should have both equal rank.
Yes.
Minus identity. Okay, thanks. Are there any other questions? So it seems that no other questions. So let's thank the speaker again. And our next item is lunch. Nobody in this room knows where the lunch is, but local organizers on the first floor should know and direct us. Hopefully, so let's guard on the first floor. This was an organizational issue for in-room people, and for online people who will leave this, will untie all this configuration and then leave the Zoom with all the breakout rooms. So you
Раз, два, три. Все работает.
Все работаю. Все слушаю.
Наш микрофон. Вот я сейчас говорю. Только слышно.
Ты что-то как-то куда скажет министерство поместить благодарность, да, поместимо. Вперед, впереди паровоза действует.
Окей. Владимир Ровенский, I hear.
Ух ты!
Okay. We have 5 minutes. Still. Okay.
I'm here.
Okay.
Good day. Добрый день.
Здравствуйте. I'd like to. We have 5 minutes.
So I need to make share screen, yes?
Yes, yes.
I can do it now, yes?
Yes, you should.
Okay.
Yes.
It's okay?
Хорошо, вы слышно.
У нас тут с глобальным потеплением.
Да, фанис.
Да.
Камера. Все включено.
Ага, вижу. Так, стоп.
Это Кенберг помахал.
Да.
Да. Ну что, ну я думаю, еще минут надо подождать. Хотя может.
Да. Zoom у нас сам по себе в полном экране.
Нет, это вопрос Владимира Ровенского. Да. Вы можете расширить полностью полный экран? Can you Ctrl-L?
To make the presentation larger somehow, full screen or something.
Full screen?
Yeah, it's kind of. It could be larger.
Okay.
Oh yeah, great.
It's okay? No.
Yes.
Great.
Yeah, actually, it was not bad.
Hello.
Приветствую, Владимир.
Добрый день, Володя.
Евгений.
Да. Пора. I'd like to introduce Vladimir Rovensky with title It's Written Geometry of Foliation. You're welcome.
Oh, okay, so I can start. So good day to everybody, and I'm very happy to see all participants and all my old friends from Novosibirsk, from St. Petersburg and other towns. So my topic is some presentation maybe of several topics, but first of all, foliations presented here in the picture of so-called rep foliation. Here, maybe everybody knows that in the torus we have infinite number of leaves, but they are diffeomorphic to plane, but boundary leaf is compact. So we can glue this to torus and obtain rep foliation of three-dimensional sphere. Okay, but this is not my topic today. Okay, and before discuss contents, maybe let's look at this photo. This photo is from the time when I don't remember exactly this year, but this is in the working room of Viktor Andreevich Toponogov. Here you see some electricity equipment, and so it was maybe in 80s years. Okay, and maybe I will read some Toponogov's advices for solving problems. These are not exactly his words. This is some my interpretation which I have in my memory. So, and this is not universal. So, the main thing is a geometrical construction structure. So, not calculations. This will be after, as I understand. The second, first consider smooth, even analytical case. The third is to solve problem is a natural setting and unnecessarily don't involve additional structures. Okay, and the last one was for me was most impressionable. Find a method that is not described in the literature and that no one knows. Okay, so maybe it will be useful for young mathematicians also today. Now about
said and done.
Yes. Okay, but there are many other advices, but I don't remember exactly. Maybe we will discuss in the special day of this conference. Yes. Okay, so first topic is about Toponogov's conjecture on foliations with positive mixed sectional curvature. And the second topic is about integral formulas for foliations. So both topics are related to extrinsic geometry of foliations. And the second topic I divided into 4 subtopics with a bit different tools, but I hope they will be interesting to participants. So now I will give some preliminaries. So I will not give more definitions. Maybe this is standard picture. What is foliation? So locally, this foliation is as a partition of Euclidean space by parallel subspaces of fixed dimension. Okay, so this field of geometry was started from time of Rep and Ehresmann, but this is not only geometry. This is a field of topology also. Okay, and the foliation I will denote by F, and it will be p-dimensional foliation with leaves submanifolds. But we know that foliation also is defined by involutive distribution. What means involutive? Means that Lie brackets of any two its fields belongs to this distribution. Okay, so distributions were mentioned in the previous talk today, so you have some impression for this notion. And in the case of distribution, also we have such notation in my slides, D, for example. So this is reference to volumes book for, say, geometry of and topology of foliations. But there are many other books, I cannot mention them here. Okay, now some notations, maybe standard. So dimensional, smooth manifold, Riemannian metric on it, Levi-Civita connection. So we have 2 distributions, and say one is D, second is D tilde. Sometimes D tilde corresponds to foliation, and the dimensions are P and N, and these are projections onto this distribution because we have metric. Okay, so what is extrinsic geometry? In 2 words, this is properties related to second fundamental form of the leaves. But in case of distributions, we can consider two distributions and also integrability tensors of these distributions. And the geometrical classes are, for example, totally geodesic foliations or distributions, harmonic, mean curvature vector is 0, or totally umbilical when, say, second fundamental form is proportional to the mean curvature vector. Okay, so my first topic will be Toponogov's conjecture. This is about totally geodesic foliations. So curvature tensor will be introduced in all topics. And this is more or less standard notation. This is Lie bracket. So Ricci curvature is trace, and the scalar curvature is also trace. So this is the function. So what is the mixed sectional curvature? This is sectional curvature when we consider two vectors, and here it is written planes, but plane intersect both distributions by one vector and another vector. So in this picture, the planes which intersect this and this distribution. Okay, so impression of mixed curvature and generally sectional curvature is the following. Then say on the surface of constant curvature, the behavior of geodesics is as in these pictures. So on a sphere they converge, on a hyperbolic plane they diverge, and on the Euclidean plane they are parallel. But this is intuitive, maybe intuitively many useful, but to study problems we need more tools and more calculations. Now, what is the starting theorem in this topic? This is the theorem from this year by Dirk Ferus, and this is about foliations with constant mixed curvature, and sufficient we can consider one complete leaf. But what is interesting that we have estimate of dimension of leaves. So dimension of leaves is less than this fantastic number. This is the number of linear independent vector fields on a sphere. So n is codimension of foliation. So sphere is somehow in orthogonal distribution, but this is not exactly this sphere. This is generally sphere. And for this number, we have some computational formula. So we can represent any number in this way, and we have such representation of this Adams number. And immediately we have such.
So excuse me, codimension is P or dimension is P of the leaves?
P is dimension, F.
Dimension, okay.
Because n plus P, we have n is codimension. Okay, thank you. So this is logarithmic estimate. So function is logarithmically, not linearly. Okay. No, so I will not give much details here, but what is the conjecture of Toponogov? So he has many problems and conjectures, and one of them is the following: that simply that this estimate is valid when we replace constant curvature by positive curvature, and this conjecture is still open for compact foliated manifolds. No, for example, we don't know if there exists geodesic foliation of some compact, any compact, I don't know which, four-dimensional manifold with positive curvature. So if we will find this example, it will be counter-example to this conjecture. No, because computation shows that P is equal 1, rho of codimension 3, so of 2 is 0, because even-dimensional spheres have no vector fields. So somehow this example, if somebody will find, will contradict to conjecture, but I hope that nobody will find. Okay, so some history. The history is that in previous years in my PhD dissertation and continuation of it, we studied, no, first of all, it was local counterexample. So local means that in the neighborhood of one leaf. So in the four-dimensional manifold, locally we have geodesic foliation with positive curvature. But for submanifolds in a sphere with standard metric, the conjecture of Toponogov is valid. So this was very nice, and I was very happy when it was found. But later on, we tried to find approach to Toponogov conjecture using flows of metric, because such flows of metrics were popular and now are popular also. This was done in this work, but in this work with Vladimir Sharafudinov, we were stopped before, say, existence of global solution, but a local solution we found somehow. Okay, so the problem is open, and what can be done now? So recently, I find some extension of this using the notion of weighted curvatures. So weighted curvatures appear when we consider on a manifold some additional, say, vector field or function. In this case, a vector field can be gradient of this density function. So I see that today it will be another talk about density functions. Okay, and instead of usual standard Ricci curvature, mathematicians consider so-called modified weighted Ricci curvature. Here is Lie derivative in direction of x. Here is to form. So this is some notation from geometrical analysis, and we can replace by this. Many problems are studied for this curvature. Okay, so what can be done for foliations or distributions? So we can introduce so-called weighted Jacobi operator. So we assume that we have two distributions in this case. And this operator, this is standard Jacobi operator. And we can see that somehow, if we assume this positive to be, this can be somewhere non-positive. So this is some small observation. And what is the conjecture extended in weighted version of Toponogov conjecture? This is the following, that again, if we consider totally geodesic foliation on a closed or say manifold, and in addition we consider vector field, and we consider such inequality, this is condition, okay? So if vector field is 0, this condition means exactly positive mixed sectional curvature. So, but in this situation, we also suppose that inequality is valid. So this is, some details are in this paper of mine. Okay, so what can be done immediately? Immediately we can extend a bit Verus result. So we can, in this result, instead of, say, constant curvature, consider this modified weighted Jacobi operator is constant, so identity in orthogonal distribution. And in this case, in addition, we assume this inequality for vector field, and we can prove this inequality. So this is valid, and this is in this paper, published years before. Okay, so this result somehow is a motivation for weighted version of Toponogov conjecture. So if you have no question, I can continue to another topic. Okay.
So excuse me, the mixed curvature is in reference to two different foliations?
Not exactly foliations. This is situation is that we consider two orthogonal complementary distributions, and sectional curvature only for such planes. Yes. One vector is here, and another vector is here, but this is only some part of sectional curvature.
Yes. Volodya, and this distribution need not to be integrable, just vector distribution.
Nice question, because in the title it is written of foliations, but in main situation, not in all. I consider arbitrary to say two arbitrary complementary orthogonal distributions. So I don't consider here questions related to, say, how they generate, say, brackets of this, but I consider some local and sometimes global geometrical properties of this distribution related with this second form and with these tensors mainly. Okay. So let's continue. So integral formulas. Integral formulas. No, everybody knows say Gauss-Bonnet theorem, but I mean here for foliations and maybe again not only foliations but for distributions. Distributions, non-integrable or integrable, doesn't matter. So these formulas, no, it is a, I think, interesting topic, and I will show some subtopics in this direction. First topic will be when, here I assume foliations because to avoid some technical computations. So foliations with a unit normal vector field. So in this case, maybe before I will say that integral formulas in Riemann geometry can be viewed as conservation laws of quantities when the metric changes. Somehow, I assume they can be applied when we consider laws of metrics. Okay, and this is right. For foliated manifolds, they relate geometry of leaves and curvature and sometimes obstructions for existence of foliations or compact leaves with given properties. Okay, and how we obtain these formulas? Usually we obtain using divergence theorem. So for some appropriate vector field, we compute divergence and say on the right hand side, we obtain some several terms. And if we integrate on a closed manifold, we have integral formula. So this is the method, no standard method somehow. But geometry is here, which vector fields we consider. Okay, so first of all, I will start with, no, maybe this is standard notation. So if we have codimension one foliation, we have shape operator as for hypersurface. And if we have symmetric or non-symmetric square matrix, we can define elementary symmetric functions. So this is standard formula. This expression is polynomial in T, and sigma I is coefficient of this degree. For example, sigma 1 is trace of matrix. This is the mean curvature in our case of the leaves. Sigma n is determinant. Okay, so we have n plus 1 invariance. Okay, sigma 0 is 1. It is obvious. Now I will give some history. History is that first known integral EIF will denote integral formula. Okay, sorry, here you don't see. Maybe I don't know how to do this, but okay. So first formula is very simple, but this means that total mean curvature is 0. Immediately we have that either it is 0 on the closed manifold, or there are 2 points with different signs of this H. Okay, so for example, if we wish to prescribe and we take function and wish that this function will be mean curvature, and we wish to find metric, so this function cannot be positive or cannot be negative. Okay, this is obstruction for existence of some foliations. Okay, the second historical formula is for sigma 2. This is sigma 1, sigma 2, and here is Ricci curvature. So this integral is 0 on a closed manifold. So again, if we assume Ricci positive, there are no harmonic codimension 1 foliations and negative totally umbilical foliations. Why harmonic and totally umbilical? Because in this case, sigma 2 will be either positive or negative. And say in first case, it will be negative, it is negative, so somehow contradiction. Okay, so these two formulas, after this forms appears equation. So can we continue this to a sequence for any sigma k? It is possible. I will show how to do it, but before, maybe I will give another amazing consequence of this sigma 1 and sigma 2. Okay, so this is a very simple example, but maybe it is interesting because both two formulas are involved. So we assume Ricci curvature greater than 2, and sigma 2 its image contains such intervals. So from 1 to 0, from 0 to 1 plus some epsilon. So the idea is that, no, first this is compact, and next we find some point where this is 0. And after some calculations, we find another point where sigma 2 is greater than 1. So this is the proof. So both formulas work. Okay, now what is the series of formulas? So to make some progress, I consider not codimension 1 foliation, but I consider foliation of arbitrary codimension, but it has a normal bundle with 0 Euler class. This means that F admits a unit normal vector field. So together, this vector field and foliation, they span distribution of dimension foliation plus 1. And this distribution is the main structure now on our manifold. This is some bundle of tangent bundle. Okay, note that in modern mathematics, this object is belongs to sub-Riemann geometry. And somehow we have foliated sub-Riemann manifold because F is inside D, and this is a little studied object. But I will not concern much to sub-Riemann geometry. I will concern only this situation which we have. In this situation, what is geometrical construction? Construction is that we introduce some auxiliary linear connection. And using this connection, we will obtain integral formula. So connection is very simple. So P will be projection onto this distribution. This is regular distribution. Projection is self-adjoint and with this property. This is standard. So after this, we introduce this vector field, analog of mean curvature, but projected onto D. And the standard shape operator, sigma elementary functions as before. And maybe we need one construction from linear algebra, Newton transformations of linear operator. So Newton transformations give us a series of T R of AN. So this is recursive formula, or this is explicit formula. Products with this sum, this is degrees of matrix and sigma of this matrix. So this is products and the change of signs. Okay, so we also need divergence, but divergence along foliation. F divergence can be applied for this transformation, but generally for any tensor which acts on a tangent bundle. Okay, so this is, in my topic, this will be called divergence along F. Okay, now it is independent on the choice of orthonormal local frame. Okay, now what we need, we need some operator, say R, what's this special R P of X, but it is produced using curvature tensor of this connection. Okay, and we can know that such summation is analog of P Ricci P curvature. In this case, we can compute divergence. This divergence is calculated by this more or less compact formula, but here we have trace, we have product of Newton transformation and this operator, not along X, but of image X under this degree of shape operator. So this is notation for, say scalar product, but X is arbitrary here. So this is can be we can extract what is divergence. Now maybe the result is the following. So for a closed sub-Riemann manifold of such view that we consider, and in addition we assume harmonic distribution D orthogonal to our D. But this is essential condition. But what is harmonic distribution? No, again, mean curvature of this distribution is 0. Okay, so we have first formula. This is analog of rep formula, but in our situation, and for other indexes, we have R2 until N, we have such formulas. So again, this formula generalizes known result for codimension 1 foliations in this paper of also my collaborators in other works. And maybe for R equal to, we have such consequence, but with this special region, which generalizes the second classical formula. Okay, so maybe one interesting consequence, usually people are interested what will be when a manifold has constant curvature. So if we assume that this modified curvature tensor is of constant curvature, but for x, y, v in D, so somehow Sub-Riemannian restriction here. So in this case, we have very nice formula that total sigma is this expression, it is independent of affiliation. So we see only numbers and volume of M. So for any affiliation, we have this. And the result for compact space forms, which is a particular case of this, was published here by these mathematicians. Okay, so somehow this is a topic about populations of arbitrary codimension, but which admit a normal vector field. Okay, now I will move to the second topic, if you have no questions. Okay, the second topic, singular populations. So for me, the word singular some time was some fantastic in my dreams. What it means? Can we work instead of regular with singular populations? And what I found first that there exists classical definition of singular distribution and singular population. So in two words means that dimension is not constant, but this is not enough. We also require that if we have such singular distribution locally in the neighborhood of any point, if we take one vector, we can extend this vector in the neighborhood of this point such that this vector field will be inside this distribution. So some extend possibility of to extend locally. But this is singular distribution. And singular foliation, no, this is such that its tangent bundle is singular distribution. But example appears in Riemannian foliations, say in this book, but not from this point of view. Okay, so we have such definition, but how to work with this? So the construction idea, no, I will give in next slide, but maybe first I will give main curvature object. This is mixed scalar curvature. So if we have distribution and Riemannian metric, automatically we have orthogonal distribution and we have such construction. This function is called mixed scalar curvature. So this is averaged mixed sectional curvature, in other words. Okay, so in particular, if we have one-dimensional distribution spanned by a vector field, so this is reached in this direction and n. Okay, so this scalar curvature is involved in many topics. I will not mention them in my talk, but there exists some, no, say, paper, articles where there are more details. So I will skip this. You can find in internet, in archive or journals. Okay, but also you can find more details in this recent book with my collaborator Pavel Valchik from Lodz, which was published this year. Okay, so why it is interesting to consider mixed scalar curvature? So we can I can recall this classical formula. So divergence of these two vector fields, H is for distribution D, H orthogonal for its orthogonal complement. But we have mixed and we have some term built from 6 terms. But these 6 terms we recognize they were before. So in some sense we can say, because of this formula, mixed scalar curvature belongs to extrinsic geometry of populations, because it can be expressed. Because generally curvature tensor doesn't belong to extrinsic geometry, but what such its part belongs. Okay, and what from here immediately we have such integral formula. This is classical formula from this year. It is well known, and there are some versions, maybe plus minus this year of another authors. So my aim is to extend, to generalize this formula for singular foliations or distributions. We can do in 2 ways. For singular and for webs, it will be at the end of my talk. It will be done. So now we need some technical tools to work with singular foliation. So the main idea or construction here is that we can parameterize singular distribution, not every, but some sufficiently large class. So we can consider P smooth endomorphism of tangent bundle, and image of this P is called singular distribution. So rank of this P cannot be constant, so we have a distribution of not constant dimension. Okay, so now we will work with this distribution, and we will consider two such endomorphisms. And two such endomorphisms give us two singular distributions, and P will be the sum of them. So in particular, if these are orthoprojectors onto complementary regular distribution, then P will be identity map. This is standard situation. But in this way, now I consider singular situation. So we need some construction of curvature here. But first of all, we will restrict our metrics and endomorphisms. So first of all, Riemannian metric will be allowed if these distributions are orthogonal at each point, and this operator are self-adjoint. This property is technical to simplify calculations, because it can be done without this, but this is essential. So we consider also allowed operators. So I need such equalities. So if we look at these equalities, we see that here, what is difference? Here is P square, here is without square. So if these are orthoprojectors, then this is automatically satisfied. So this is some extension of class of orthoprojectors. So we have such assumption. Okay, this is done in this paper with Paul Popescu. Okay, now to consider some curvature, we define such mapping. So we see here projected, not projections, P2, P1, and P. This construction is some similar to construction of curvature tensor, but there is some difference. And using this sum, what we have that this is tensor. So generally, this is not tensors, and without our previous assumptions, also these are not tensors. But with assumptions, this is tensor, and we can define finally what is the mixed color P curvature in our situation. So you can guess that we are almost before our integral formula, but maybe first we need also some divergence type theorem. So we need to define divergence with respect to P. So it is defined in standard way with this. So using this connection, so-called. But when we have divergence theorem, not always, but if we assume this property, the divergence of P square as operator, this is usual divergence, is 0. This is somehow the same as this theorem, and we can integrate. Okay, I cannot give proof now, but now we can move to tensors. We defined in a standard way using these operators H1, H2, T1, and for second distribution also, because we have two distributions, modified curvature. And what we can do on the last step? On the last step, we also need norm, but norm will be so-called P norm. It is defined by this way. So for X, image P1 and image P2 together, and this is enough because in our formula, each vector will be exactly in this class. And so we have such a formula with divergence P, and here is mixed color curvature, and this is formula very similar to classical, but it is a bit different. So integrating, we have, we need to assume this property, and we have integral formula. So some consequences P autoparallel. No, this is the game when some negative terms are assumed to be 0 and positive, and if this is positive, for example, then we have that because integral is 0, that everything is 0. So we have this consequence. This is very elementary. So let me stop at this point with this topic. Okay, so what was interesting here, from my point of view, that we consider another connection and we modified curvature and norm. And but for classical case, this formula reduces to well-known formula. Now we can continue to work with singular distributions, and this is a more delicate topic, so-called Bochner-Weizenburg type formula. But this is related to Bochner technique. Classical Bochner technique in geometrical analysis shows that parallelism of some tensors which lie in the kernel of Hodge Laplacian on a closed manifold. So I don't show here formula, it will be later on in my topic. So what we can do? So first of all, we continue with singular distributions, but now we work with another, no, this is not exactly linear connection, but this is some map which will be used to build some tensors. So this is not connection, but we can define this object for functions and for tensors. First for 0, 1, and then using product row, we can define this action on tensor, no, for any tensor. And tensor is parallel if this is 0. This is obvious. So this approach is published in another topic with my collaborators Paul Popescu, Sergei Stepanov from Moscow in this year. Okay, so details are there. But here I will give maybe similar as before. We have some definition of P, but difference that only here is P. And so condition is divergence of P. Before it was P squared, here is P. So these conditions is enough and sufficient for this formula. No, in this formula, nu is inner normal to boundary, but without boundary, we have simple formula 0, if without boundary. So now we will work with some tensors. So how to produce analog of Hodge Laplacian? We need some definitions. First of all, P connection Laplacian. This is product, but in this product, this is unknown. So we define by this way as sum of on any vectors. So this is defined. We have this, and this condition divergence P is very important, because if it is holds, then this is L2 adjoint to nabla P. No, we consider closed manifolds in this case. And for example, this is analog of standard maximum principle, that if this is negative, then it is parallel. So the proof, maybe I will in 2 words show that here we construct one form, and we use our divergence theorem before, because so integral will be 0, so we have our L2 adjoint property. So this is a standard technique. And maybe I can mention that in some Riemann geometry books, this is the similar proofs is for classical, say, formulas of this kind. Okay, now maybe some additional more than 2, which is very useful here. So this is so-called almost Lie algebraic structure. So why it is interesting? It is interesting because generally, without almost, we also have Lie algebraic structure. This is more general. This is similar as, say, we have complex manifolds and almost complex manifolds. So here also. So first of all, we have morphism from some vector bundle over M to tangent bundle. And in this case, it is called N-short. Okay, no, this is terminology. But what bracket is very useful notion. So because we are not on the same vector bundle, we need some bracket operation. And we have 3 axioms, 3 standard axioms. So this is skew symmetry, this is Lagrange rule, and this is also some relation with rho. Okay, and the last one, somehow we can introduce such an operator difference, and the last means that this operator is 0. This operator will appear, but we will remove it at the end. Okay, so this morphism rho together with bracket is almost the algebraic structure on a vector bundle. So if our distribution are integrable, somehow we have Lie algebroid, but I will not give more details, but only question, maybe you can guess now why this structure is needed, because before we considered P operator from Tm to Tm endomorphism. So this is exactly why how we have this structure. Now in more details. So in our case, we have P, this is endomorphism from Tm to Tm, and we define bracket, we need this bracket, and we define in this way. So this is simplest definition. I don't know more simple, but this is enough for us. So this, how using this map, we define bracket. Okay, and now with this condition, so axiom 3 in almost product, this means in this way, so that this is 0. And this is the same as nabla P. P is symmetric tensor by its covariant components. So it can be proved, and together we can say that this bracket, if this holds, defines almost Lie product algebroid structure on this object, which and so we can use some ideas of this structure. No, okay. So now using these ideas, we define operators dp and delta p. So using this nabla P, I will not give more details, but we can say that this operator can be called Hodge type of Laplacian delta P, and so P harmonic forms. And if this condition holds, divergence P on a closed, then this is adjoint to this. So this very nice. That's exactly what we need to have with nice properties of this operator. So for functions, this is Beltrami type operation, and no, for functions we have somehow standard result, but this is only nabla P 0. So we cannot say that f is constant. This is constant along distribution somehow. But I can say that if distribution is bracket generating, then it is constant on the whole manifold. But these details I will not give more. So now we define curvature using this nabla P and Ricci. Okay, but why we need this? We need this first of all to see how it acts on tensors. Generally, it acts by this way. So we have here dp. But if we assume this condition, so before we will assume both two these conditions, divergence and symmetry of them. So in this case, this acts by the second line only. This disappears. Okay, so using this action on tensor, we can now finally construct so-called Weizenburg P curvature operator on tensor. So it is constructed by this way for arbitrary tensor. Okay, and I can say that if in this definition we use usual standard curvature R, then we have standard well-known Weizenburg curvature operator. But here we have so extension for distributions. And the result is very similar to classical. So we have such decomposition. Okay, so Hodge Laplacian is this Laplacian, but plus curvature term. Okay, and but this is not the final is this formula. This formula is Laplacian of this function, norma of omega. So this is applicable to any omega. And using integration on a closed, we have also integral formula of this way. How to work with this formula? Similarly as in classical Bochner technique. So if we assume that this is self-adjoint and positive, okay, this is positive. So this is positive automatically. But here we assume that omega is in kernel, so it's P harmonic. So this disappears. In this case, we have that this should be 0. So this is so-called vanishing theorems. The question is under which conditions we can provide these properties. So this is the final slide in this topic. If you have no questions, now I will move to a bit more easy topic without such, say, singular distributions. this is topic for webs of foliations. So why webs? No, webs is more or less classical object, but we will look so in a classical way that web is we consider orthogonal decomposition of standing bundle to several, say, k greater than 2 distribution. So it can be orthogonal, and it appears in modern topics of Riemann geometry, so multiply twisted or warped products, webs of foliation, and hypersurfaces with a constant number of different principal curvatures, so-called Dupin hypersurfaces, for example. And I will recall only classical, well-known for 2, but for k arbitrary it is also known. This means that if each is parallel, so integrable totally geodesic, then locally this M, the structure is decomposed in the product of manifolds. Okay, so the question is how to find sufficient condition for such decomposition, maybe using some assumption on curvature, on mixed scalar curvature. So the question is, what is mixed scalar curvature? So in this case, we define also this object. This is extension of classical. First of all, we use adapted orthonormal frame. No, simply first part from D1, then from D2. So we distribute this frame among all these distributions. Okay, and the mixed scalar curvature is averaging for each pairs of such curvature. So what is SD, DI, DG? So for 2 distributions, we consider the sum of mixed sectional curvatures for these distributions. And then we consider for each pairs, DI, DG, different pairs. So this is well-defined object. And for k equal to reduces to standard definition. Now, example maybe what is multiply twisted product. So maybe I have enough time. So this is also a generalization of the situation for 2 objects, for the product of 2. So one is so-called base, and here are F1, Fk, and this is warping functions, and the metric is some change of metric of product with these factors. Okay, but what is function? The function U1 and etc. This is functions not on the whole manifold. This is function on F0 and Fi. Okay, so these are smooth functions. And if these functions are only on F0, then we have multiply warped products. So this object, I looked at recent papers on many authors. So this is popular, and many authors studied curvature, Einstein equations, and etc. on such kind of objects. Okay, and on this object we can also calculate the mixed scalar curvature using Laplacian of this function. Okay, now the aim is to extend, say, previous formula for 2 distributions to the case of k distribution. So it can be done more or less automatically. We only need to mention or to observe such useful formula that this curvature is the sum of this. So for each di, we consider mixed scalar curvature for this distribution. And after summation, we have twice our new mixed scalar curvature. So the proof is linear algebra, not more, but you can guess that using again somehow linear algebra idea, we can combine and obtain integral formula. Now, first of all, we will define maybe again orthoprojectors on these distributions, second fundamental forms for each, but we also define for pairs. So what means, say, IG? This means for distribution di plus dg. The same can be done for triples, etc. Okay, but at the beginning we don't need this. And what we can say? We can say that the following formula is valid on a closed manifold with k complementary, orthogonal, and regular distributions. So what is this terms? So this term is the same term as was for one distribution, which was before. Okay, but here we have summation. And the proof is, first of all, we compute divergence of such vector field. So this is the sum of vector field of di of its complement and for all I. And this, so result is in this paper with more details, such journal in Romania. Okay, and finally, maybe we can give some applications. So we can consider mixed totally geodesic distributions. This means that we consider pairs. For each pair of the IDJ, what this AHIJ is 0, so-called mixed totally geodesic. And mixed integrable is similar, but for tensor integrability of this pair. Okay, so somehow decomposition, but not complete. And I recall the formula that we have. And using this formula, we have such applications to splitting of manifold, related to the RAM decomposition theorem. So in the first, we have assumption so that distributions are integrable, so foliations and harmonic. And now you can see that if they are harmonic, so positive term 0 and this 0, we have negative H. So if we assume that S is non-positive, then it will be 0. This is done non-negative, yes. And similar, if we assume umbilical distributions with additional property orthogonality of these vectors, now we can say that assumption that mixed color curvature non-positive yields that it splits. Now immediately we have application for multiply twisted products. Okay, all details are given in this paper. So thank you for listening, for participating who was here, and thank you very much again. And I can also say my greetings to organizers and wishing for successful conference. This was I need to say in the beginning, but I say at the end. Thank you very much.
Thanks a lot. Is there any question from internet? Feel free to unmute you. Okay, maybe.
Yes.
Yeah, just feel free to unmute and ask a question. I don't have anything.
Okay. Okay, let's thanks again. Maybe. Okay. And we have 3 minutes of break, and then before the next talk, it's the next speaker is here.
Yes, I am. Hello, everyone. This is Wilderich.
Thank you. Okay. You can demonstrate your screen and so on.
Yeah, so am I already, say, Joscha, can I already share the screen or?
Yes, I think.
You can screen share anything you would like to show, any window essentially.
Okay, let me try.
If you have PDF slides or something, just open them in some Acrobat program and then
so
share screen. And
I'm still trying, but so wait, let me see.
Yeah.
So
one moment.
Let's see. Yeah, it takes some time, but I hope it's going to connect now.
Running in sharing, but there is nothing on the screen here. Just this information.
Yeah, I'm still trying to connect.
Well, what is your operating system, by the way? Windows?
Pardon me? So this is, yeah, so I'm using Apple devices, but that's sometimes and now it doesn't, it says it doesn't want me. All right.
How Zoom works on Apple computers. Why does it take so long to share a screen? It usually doesn't. It doesn't. The other thing is,
So I hope something's going to work now. Okay, yeah, that should be my title. If you can see this now.
Okay, yes,
yeah. Okay.
Okay, let me introduce Wildrich Tushman with spaces and modular spaces of non-negatively curved Riemannian matrix. You're welcome.
Yeah. Oh yeah. Yeah, by the way, so I hope now you can also see me. I'm still struggling with some stuff, but okay, but at least you should see the title. Yes, so welcome everybody. And first of all, let me say thank you to the organizers for inviting me to give a talk on such a special occasion. And I think it was quite, a lot of work to organize such a big conference. Unfortunately, even if I planned before, I couldn't make it in person to St. Petersburg, but I hope I can now do my best to somehow still present some things I would like to relate to you. So I have again now problems that, can you still see? So the funny thing is on my own screen, it says I should still connect. So I'm not sure if you can see the title at least of my talk, as it appeared there before.
This is just some instruction for users.
Yes, I hate online talks. Sorry, I wish I just had the blackboard. But anyway, so supposing you really see now the title. So let me start with the plan of the talk itself.
No, we do not see the title of the talk.
You don't see, okay.
No, we're not sharing.
Okay, now, can you,
Please see on your iPhone or iPad, connect to Wi-Fi network and so on. Tap screen mirror, choose Zoom WP.
Yes, so that's why the connection is gone again. So in the worst case, I don't know what's wrong here. It tries now to reconnect.
Is it online document, right? Is it correct to guess?
Yeah, sometimes Zoom uses extra allowances, but I actually made sure that should work. So now, are we now back?
Besa.
Okay, so, okay, hallelujah. So, okay, so once again, so I'll be speaking about spaces of modular spaces of Riemannian matrix with a special emphasis on lower curvature bounds and in particular non-negative sectional or Ricci curvature, since this is a huge field indeed. So let me start to just give you a basic plan of the talk. I will first introduce all relevant objects and notations in the first part and try to also motivate why one looks at these things, and then we'll proceed with basic results, but also open questions, especially in lower curvature bounds. And in the third part, more related to comparison than Riemannian geometry, maybe I will try to sketch a broader and non-traditional approach to the study of modular spaces through Gromov-Hausdorff space and convergence. All right, so let me start with part one. So in all what follows, so we will be dealing with smooth manifolds, always finite dimensional, and they can, however, be either closed or also non-compact, depending on what topic I'll be speaking about. Well, so to start, in principle, with modular spaces, you can also view it in such a way, in general, even myself, I spent decades sort of my professional life to construct special metrics with certain, say, curvature properties or constraints, or on the other hand, instead of constructing, obstructing them or find obstructions to the existence of, say, positively curved metrics. However, it's like with many other things in mathematics. So once sort of you know you have your solution to a problem, you might also wonder how many solutions there are. And of course, this also must entail that you make sense of how many actually is. So if you have, say, one metric with a sort of, say, positivity condition, you can push it a little bit. That's an open condition, so we'll always have an infinite number. And so you must make a sense of how many actually means. So what we will do for such a given smooth manifold is looking at R of M. R is standing for Riemann. And this is simply, first of all, just the set of complete Riemannian metrics on our manifold. So, and this is now just the set, and as I said, in general, always an infinite or even uncountable infinite set. So now you must first of all make it into a space to talk about, say, its topological properties, to measure complicated structures or make sense of what numbers should be replaced by. So to make it into space is easy. You simply can view it as a subset of, say, all symmetric bilinear tensor fields on your manifold. So as a subset of just the smooth sections of the second symmetric power of the cotangent bundle. That's just a vector space, and it has a natural topology. So you look at this, this equipped with the smooth topology of uniform convergence on compact subsets. And I hope you can see this already now. And with the induced topology, this is called the space of metrics.
We have problem.
So, and here I see again, yeah, they want me to reconnect. I don't know what's actually happening and why this always is interrupting. So I hope now we are back. So we look, so the set of Riemannian metrics on M becomes now a topological space by viewing it as a subset of these vector space of sections. So this is a space of metrics. And actually, here's the first remark. So you can add metrics, you can multiply them by positive reals. So in particular, your space of metrics is, if you don't impose any other restrictions, it's just a linear convex cone. And as a cone, it's contractible. So topologically, it's totally boring and uninteresting. However, the situation will change when we are looking later on or soon on subspaces which satisfy certain curvature conditions. But I put here, this should be self-explaining. For instance, this is the space of Riemannian metrics on M with non-negative sectional curvature. This would be Ricci flat matrix. This would be positive scalar curvature metrics on our manifold. However, there's another thing, another important object we also will have to consider, which from geometers actually makes even more sense than just looking at the space of metrics. Namely, now the modular space comes into play. So everybody knows that, for instance, if you do hyperbolic geometry, there's dozens of different models, say, for hyperbolic geometry. Namely, there's a Poincare model, this model, the upper half-plane model, many, many other things. And of course, they look different, the metrics, right? But they are all isometric. And this is really so when now looking instead of individual metrics at the really genuine different geometries you want to find and understand on a manifold. And for this, what you do is you notice that the diffeomorphism group of your manifold acts on the space of Riemannian matrix simply by pullback. And so you can quotient out this action, and this will then lead you to the moduli space. So the space of matrix quotient out by the action of the diffeomorphism group by pullback. And here you just take the quotient topology. So this will also be a nice topological space. Maybe not that nice because it has quite some singularities in general, but this is now the moduli space is now the real space you are interested in. It's a space of different geometries your manifold allows. So why is it complicated? This is simply due to the fact that the action of the diffeomorphism group can have many different non-trivial isotropy groups. Yeah, so for instance, here, what I'm writing here in blue on this picture is, so this could be our whole space of metrics, but now we take a fixed metric G here and look at the orbit of G under the action of the diffeomorphism group, and then by construction or by the very nature of this action, so the isotropy group diff M in a point G is nothing else but the isometry group of the metric itself. So as soon as you have a very symmetric manifold, or say you take some metric, average it over the action of a compact Lie group, you will have non-trivial and also positive dimensional isotropy groups, and so the moduli space as a quotient can be rather complicated. Okay, but now at least we have not just sets, but we have spaces of metrics and spaces of geometries, and now we can make sense sort of to saying how many metrics, how different metrics there are by looking at the topological properties of these spaces. And this is sort of what will lead me now on to the next part of my talk. So that now I will mostly focus on metrics with some sort of non-negative curvature and what can be said here. And indeed, this has quite a long history, the subject. And so first of all, let's consider this question again: how complicated can a topological space be? And this most basic questions you can ask about a topological space is it connected or not? And if not, how many components does it have? And to give you now some sort of flavor and introduction to these questions about moduli spaces, let me start with some connectedness and disconnectedness result. Indeed, there's the very first, very old result going back to Hermann Weyl. In 1916, he published a paper where he showed that the space of positive sectional curvature matrix, so the space of positive Gauss curvature matrix on the two-sphere is connected. And this was actually sort of one of his attempts to solve one of the famous problems named after Weyl. Yeah, so namely, there is a so-called Weyl problem. Any regular metric, so a certain regularity of positive Gauss curvature on the two-sphere, can be realized by a regular convex surface in R3. Or you could also say you can sort of look at isometries of the ambient space, which should induce such a metric. So that's the classical Weyl problem, and at that time, Hermann Weyl, he sort of gave a very constructive way to join a positively curved metric on the two-sphere just with the round metric. And one should also note that at that time, actually, there was not a general, say, uniformization theorem available. So nowadays, you could either do this, and for any closed surface, say, you could obtain the analogous statement just by uniformization, or if you want to run the Ricci flow, you would also see that governed, say, by the sign of the Euler characteristic, the flow will run your initial metric in the one with constant sectional curvature. However, here is also something I would like to note. So it took quite some time to solve the Weyl problem, first in the analytic case. Oh, and here we get again kicked out. I'm sorry. So are we back? So it's still trying to connect. I hope you can see it again. So let me put here the what I have to say still here. So the Weyl problem itself was first, but just for analytic metrics, solved by Levy in 37, and only in 53 in full generality by Pogorelov, building on work of Alexandrov's and convex surface theory, and as well then independently Louis Nirenberg. One should also say that that was 1916. So after Weyl published this paper, sort of he was taken in from ETH Zurich to the German Wehrmacht to join as a soldier. But luckily, sort of he could soon get back again, but then simply lost interest and worked on problems in, say, general relativity and symmetry. But this so far is the very first sort of general result I'm aware of about the space of, or modular space, here a space of metrics. Now let me make a huge jump in time. So let's go on to a result from 2002 by Fernando Coda Marquez. He looked at positive scalar metrics on closed orientable three manifolds. So that's basically besides the sphere, that's spherical space form, that's a product of S2 times S1, that's any finite connected sums of those, and he obtains there also a connectedness result. So for any such three manifold, the modular space now, not the space, the modular space of positive scalar curvature metrics is connected. And this is a very non-trivial proof. I will say a little bit later on that. So what about dimension 4? In dimension 4, there's a result by Daniel Ruberman using Seibert-Witten theory, which shows now the first disconnectedness you can have around. So it says for all natural numbers capital N, there are closed four manifolds. They are always non-orientable. In particular, they are not simply connected. So for all given natural numbers, you find closed four manifolds for which here by pi 0, I mean just the, sort of the number of components we are talking about here, so that the modular space of positive scalar curvature metrics on this manifold indexed by capital N is bigger than N. So you can produce any number of finite components in dimension 4, which already means that these metrics, if they lie inside different components, must be quite different, because there's no way to continuously deform them into each other. Starting from dimension 4, then the story sort of goes on in all dimensions. But let me first say there's an important open problem still not solved so far. Maybe nobody knows anything about the space or moduli space of positive positive scalar curvature matrix on the fourth sphere. So this is completely open. So starting now from dimension 5 on, there's a very nice result of Botvinnik and Gilkey from 96 saying that for any linear space form, which is not itself a sphere, so in particular not simply connected, well, starting from dimension 5, actually the space of the modular space of positive scalar curvature matrix on such a space form has always an infinite number of components. So these spaces, even if it's special manifolds, they can already be, in that sense, even in terms of just the components, quite complicated. And there's an analogous result by a PhD student of mine, Philip Reiser, just from 2019. You can also look at the problem which topological space forms do admit positive scalar curvature, and there are certain criteria for that. And actually, you can then show that the Botvinnik-Gilkey result also holds for any topological space form under the same dimensional restrictions that allow positive scalar curvature. So let me now say just a little bit. We are still now dealing with connected components. So the basic tools here are all rather complicated. They involve Ritchie flow with surgery developed by Perelman. This is what Fernando Coda Marquez does in dimension 3. Huberman for four-dimensional manifolds uses a lot of Seiberg-Witten theory, and Botvinnik, Gilkey, they use certain eta invariants and how to express them by the Atiyah-Patodi-Singer index theorem. So I do not, just for reasons of time, not want to go here into any details, but here is one more geometric tool where you can make a little or come to grips. So as an aside, because I will be mostly talking about closed manifolds, let's now look at open manifolds with non-negative sectional curvature, where we also have important contributions by Toponogov. So here's a result by Vitaly Karpovich, Anton Petrunian, and myself. So first step in 2005, and it was strengthened by Iga Balegradek, Korsik, and Schulz. And in 11, it says the following. So for all dimensions, at least 22, or what they did, improving it to at least 11, there are non-compact manifolds for which the modular space of non-negative sectional curvature matrix has an infinite number of components. And say the basic tool now actually to show such a result is
something.
Okay, we are out again. I'm sorry. Yeah, this is really. I'm always wondering if this could be related to some sort of screensaver, but problem. But usually it always works that way. Okay, so the basic tool is the following. It's based on result of Viktor Toponogov, and also makes use of the Sharafutdinov retection. So if we have on such an open manifold two matrices with non-negative sectional curvature, if their soles are non-diffeomorphic, then the equivalence classes of these matrices in the modular space must actually lie in different components. So the soles, they always, of course, since by the Soule theorem, your manifold does always retract onto the soul. So all souls have the same homotopy type, but if they are non-diffeomorphic, the matrix they are belonging to must lie in different components. And to give you here an example, what this could mean in very concrete terms is, now take any exotic 7th sphere, which admits a metric of non-negative sectional curvature. And by the latest works, so starting from Komol-Meyer, who constructed the biquotient exotic sigma 7, yeah, then by more work by Grube-Siller, and just recently, like 2 years ago, Sebastian Goethe, Martin Curran, and Ravi Shankar, any exotic 7th sphere indeed does admit non-negative sectional curvature metrics. So you take now any of these spheres, and now you look at what happens when you cross the sigma 7 with the Euclidean 3 space. So we are looking at S7 times R3 or sigma 7 times R3. And what Milnor actually showed that these non-compact 10 manifolds are diffeomorphic. And of course, just by taking the product metric, yeah, from these factors, they both have metrics with non-negative sectional curvature, but their souls are either the standard 7th sphere or the exotic one. So on one is the same manifold that's coming from Milnor. On this one single 10-dimensional non-compact manifold M, we have two non-negatively curved metrics with non-diffeomorphic souls. So these two metrics must then, from what I said above, lie in different components of the modular space. And in particular, to take any sort of any of the other exotic spheres, so then you will see that for M, this space has at least, say, 28 components. If you don't count orientation, or it might be different. But in particular, so this is a very simple geometric sort of way to distinguish different metrics now in the non-compact case just by their souls. Okay, and now you can also, I just mentioned this as an aside, to leave the disconnectedness or connectedness story and move on to higher and other topological invariants. Here's another result which covers also the open and the closed case. So in by Michael Wiemeler and myself, it says starting in dimension 7 for closed or in dimension 8 for open manifolds. So starting from these dimensions, there are infinite sequences of closed or open manifolds which have pairwise distinct homotopy type, for which the spaces and in particular the modular space.
Sorry?
We go again. Yes, I'm aware. It's again kicked me out, or not me, but the picture. So now it's reconnected. Okay. So in every dimension of these dimensions, there are infinite sequences. In a given dimension, infinite sequences of pairwise distinct homotopy type, for which the modular spaces of non-negative sectional curvature metrics have an infinite number of components. And the same is true for modular spaces. Then you have to modify the examples accordingly of non-negative Ricci curvature or even Ricci flat metrics. And this builds on previous work by Anand Desai, Stefan Klaus, myself, Anand Desai, Gonzalez, Thomas Schick, David Weiss, again, Igor Beleg-Radek, and many others. However, yeah, well, one can even drop a little bit the dimensional restrictions. Carla Garcia, in her PhD with me, she showed you can at least drop it by 1, and there might be different ways, again, to come over. But so far the disconnectedness story, and now let's move on to say higher homotopy groups. Can one also say something about these spaces? And yes, one can. There is a lot of things to say in positive scalars. There's, like by Tom Farrell and his co-workers, also a lot known in negative sectional curvature, but it was not so much known again in non-negative curvature. Well, so as I said, the last result with Riemann and also next one, both employ very importantly sort of Toponogov's splitting theorem for non-negative sectional curvature. So meaning that if you have an open non-negatively curved manifold which contains a straight line, so for any 2 points, right, the distance is minimized by that geodelic or that line, then the manifold splits actually isometrically, so as a Riemannian product of some Euclidean line, and then a factor of dimension 1 lower, which then is non-negatively curved as well. And by induction, of course, then you can split off all Euclidean factors so that you can come, and then your n is of the smallest possible dimension. And Giger and Gromol, of course, then extended Toponogov's splitting theorem by different means to the setting of non-negative Ricci curvature. And I also see Joost Eschenburg, hello Joost, in the audience, and he and Ernst Heise gave yet another very nice proof of the splitting theorem, which also carries over to some parts in the Lorentzian setting. Anyway, so Toponogov's splitting theorem is here a very basic tool, because even when working with closed manifolds, we have to go up to the universal covering. And if we do it correctly and nicely, we can then see and use the splitting, and because it's isometric, to again come down to the modular spaces and be able to define certain sections which relate the topology of general spaces to ones we know, for instance, flat tori, which are also investigated in the setting. So the next result now is, this is dealing now with higher homotopy groups. It just says, so in every high enough dimension, they are closed respectively open manifolds with non-negative sectional, well, for which the modular space of non-negative sectional curvature matrix, and here we are interrupted again. I'm trying to see if I can do some other connections. So this simply means I should speed up your talk. So all right. So shortly, so there are, so for higher homotopy groups, we show then that actually there are manifolds for which the modular space of non-negative sectional curvature matrix has rationally non-trivial pi3 or third cohomology, namely being isomorphic to Q. So, and this is something one would also understand better for other homotopy groups, because, as I said, like there's many results in negative sectional curvature where you can actually come up with infinite numbers of non-trivial homotopy groups for these spaces. However, mostly they are finite, so that rationally they are zero. Yeah, this is especially true also for the space, but not the modular space, because quotienting out the diffeomorphism group destroys, using the techniques used there by work of Belegradic, Farrell, Karpovich, and also Thomas Schick and David Race. Yeah, one aside is that all our manifolds we are working with to construct these examples or get these results are manifolds for which the fundamental group is infinite, and we don't have any idea how to carry this over, since we use the splitting theorem in a way that requires non-simply connectedness, whether this can sort of carried on to other manifolds. Yeah, interesting is maybe also because this is always a little mysterious. This result also carries actually over to modular space of Ricci flat matrix. However, I want to here instead relate to you a result by David Degen, PhD student of mine. He just proves the following. If you look at the very concrete Kummer surface, so and its modular space of Ricci flat matrix, they are then always scalar, and this modular space is finite dimensional, depending if you take into account normalization of volume or not. It's 57 or 58 dimensional. So even if you look at it just from the smooth side, smooth scalar matrix, which are Ricci flat, or orbifold matrix, which appear when you look at convergence and degeneration phenomena, then this modular space is simply connected. However, it has non-trivial second rational homotopy group. So, and then again, you can also use this, of course, say to come up with examples in higher dimensions. But the K3 surfaces are always, also in terms of algebraic geometry, very, very nice and still mysterious objects. Yeah, so nobody has seen a Ricci flat matrix there really sort of explicitly. It all comes from Yau's solution to the Calabi conjecture. Anyway, so I hope there won't be too much dropouts again with the internet connection. In the third part, as I said in the beginning, I want to at least sketch a little different, non-traditional approach to modular spaces based on results from comparison geometry, and where we sort of also leave sort of the stage of just looking at the space or modular space of matrix being equipped with the topology, say, of uniform convergence on compact subsets, but there can be many other topologies. It doesn't have to be the smooth topology. One could also think about Lipschitz topology. But when it comes to modular spaces, it also is natural to look at it from looking at these metrics or isometry classes of metrics as being just a natural subset of Gromov-Hausdorff spaces. So if you look at manifolds or if you look at Gromov-Hausdorff distance, you always identify isometric spaces. So Gromov-Hausdorff distance gives you a metric on the set of isometry classes of, in particular, say, Riemannian manifolds. And since the modular spaces are exactly, since we quotient out the action of the diffeomorphism group, they are always considered up to isometry, we can view the modular space of metrics of a certain kind on a given, say, closed manifold, to keep things simple, just as a natural subset of Gromov-Hausdorff space. And then can look how look at some sort of boundaries, or how can one relate manifolds here. So let me just try to introduce one two necessary concepts here. First of all, to make sense of this, so let's look at the following definition. First, rather general, but I will immediately give you some examples. So now we fix the closed smooth manifold and define ISO of MCL. So C is a set of geometric constraints, and L is just some real number. And so the constraints that could be constraints on curvature, diameter, volume. So we want them that, so these constraints C are for some L bounded by L, and we will get rid of the L soon. But now our set of conditions we are looking at has to satisfy two very important conditions. First of all, we have pre-compactness under Gromov-Hausdorff convergence. This is the first one here. And secondly, so whatever metric we consider on our manifold, there is some real number. And here we go again. I'm sorry. I'm trying to reconnect already. So secondly, for any metric we take on M, there is some real number that G is contained in ISO MCL in the set of isometry classes. So what can we do with that? We now look first of all at ISO bar, and let it be the Gromov-Hausdorff closure, yeah, which is guaranteed to be sort of nice by our first condition on C. And now we just take the union over all such L. This is the next object here. So, and of course, taking this union means that what we get is independent of L itself. So, but the good thing now is, so this I want to say in this remark, so this letter object defined by our pre-compactness condition doesn't depend on any special value of this L anymore. However, any metric we take on our manifold, for this one, we know it can be approximated uniformly or in a controlled uniform way by a sequence of Riemannian metrics, even if it's maybe a limit metric of less criticality and so on, which satisfy our first conditions here. So, no, for some L. So this is something which makes this set, on the one hand, independent of L, but on the other hand, whatever we have in its closure, we can approximate uniformly by metrics, smooth metrics with given nice curvature constraints, conditions C. So maybe now it's time for examples. The examples and the names come from major work of these people who have worked, for instance, on finiteness results in Riemannian geometry. So so these are all examples for C. So C1 is now what is given by the conditions which appear in Giger's finiteness theorem for Riemannian manifolds. So we have both-sided bounds on sectional curvature, we have an upper diameter bound, and we have a lower bound on volume. I just put it differently to make it fit into this C of G is less than or equal to L. Another condition, the very general one, appearing in Gromov's pre-compactness theorem for manifolds with lower bounds on Ricci and upper bounds on diameter, which again has also generalization, say, to pointed Gromov-Hausdorff distance where you don't need, of course, diameter bound. Here's another one, Giger-Fukaya-Gromov conditions. These are conditions which actually allow for collapsing as Gromov conditions, because there is no lower bound on volume or injectivity radius, but you have two-sided sectional curvature bounds and an upper diameter bound. Here's another one, from Perelman's sort of second preprint. He obtained the generalization of Giger's finiteness results for Alexandrov spaces, and that of just a lower curvature bound. So this also is a typical example here, lower curvature bound, but now also giving finiteness for Alexandrov spaces, saying is an upper diameter bound and lower bound on volume. And here would be another one. Now they're just looking again in lower bounds on Witchy, however, ruling out collapsing. So this is what Chiga coding in a number of papers investigated very deeply. All right, so this is one. So what can we do with that? Now we can sort of look at the following. This is maybe the last concept I would like to introduce. So we call now, if we are given two closed manifolds with some set of metrics and curvature constraints. Now we take the same C here for them. We call them neighbors if their respective isobar closures have non-empty intersection. And if we have anything inside this intersection, this sort of is a gate space between these. So this could be M, this could be whatever M prime, and here somehow is a gate, yeah, relating them. And these gate spaces, so don't think too much about Star Trek, that's not what I want to say, but these, since they are sitting in this intersection in the of the closures, they play a special role somehow and can relate these spaces. Or it's also interesting to know if there are none of them. So here's an example. If you have C1 neighbors, that's the Chiga conditions. So bounded sectional curvature, lower bound on volume, and upper bound on diameter. This is then simply because of Gromov's convergence theorem that these manifolds, if they are close enough, they must be diffeomorphic. So in particular, yeah, for non-diffeomorphic manifolds do not have C1 gate spaces at all. However, here's another extreme. Well, what you can also have, that's what I alluded to shortly before. However, in the closure, this is also related to work on to make really sense and get the best out of Gromov's convergence theorem, and there was many people working on that. So on the US side, but from the more geographic viewpoint, especially Igor Nikolaev, who's also here at the conference. Yeah. So you look you will see that even under these Chiga conditions, the limit metrics will in general not be smooth. The best what you can hope for is C1 alpha with alpha between 0 and 1. For instance, what can happen is you look at a round sphere and you let it use, and you can everything do with nice smooth metrics. So you don't change the topology whatsoever. So the sphere stays always topologically diffeomorphically a sphere, but you make from the sphere now using just nice smooth metrics, you make it more into an ovaloid sort of, and then you go on and you make the ovaloid in the middle, say just a cylinder, and you cap it off with hemispheres. So this should be here. Sorry, now I'm even erasing some stuff. This should be. So this, you make it here into a flat cylinder, and here you have hemispheres, sort of. So now it's getting even worse. Yeah. So let me make it better. If it will work better for. So you have a cylinder, you cap it off with hemispheres, say, this side. And what happens here is that, of course, in the middle where the cylinder is, it's flat. So there the limit metric has zero curvature, but in the hemispheres, you say make it to have curvature positive, say constant to 1. And since curvature is depending on the metrics like in a C2 manner, you know this limit metric cannot be C2. Yeah, so this is just C1 alpha. That's the best you can hope for. So this is something, just one example, what happens even if you don't have collapsing, you have lower bounds on volume, or in that Cheeger setting, equivalently lower bounds on injectivity radius. But now if you look, say, at flat manifolds, just tori, or even more general, almost flat manifolds, you know you can collapse them with a uniform absolute bound on sectional curvature. You can shrink them to a point. So for two flat manifolds, they are in this sense C3 neighbors, but the gate space here is a point for any. So any almost flat manifolds of any given dimension are related in this way, just rule setting. You can make more complicated examples where you ask if it's positively, say, pinched. Do you only drop down in one dimension? You can look, for instance, at Alof-Wallach or Eschenburg spaces, which are with uniform pinching collapsing to a six-dimensional manifold, so of codimension 1. I hope the screen will be back soon to you again. Yeah, but there is
I should mention
many things. Can you see again?
Your time is up. You should just finish.
Yes, okay, I'm done. So almost. So here's one more question. And this is what we just saw with Perelman conditions. Can, under lower curvature bound, just the lower one, upper diameter bound, say, and lower volume bound, can you again, can you have non-diffeomorphic C4 neighbors? If not, you would get that if you have sequences of Alexandrov spaces converging to a fixed one, or manifolds converging under lower curvature to a fixed, say, Alexandrov space, you could give a unique structure on this. And by results from Grove-Peterson, this actually would then improve the Grove-Shiohammer diameter sphere theorem. So if you have a complete manifold with sectional curvature bound from below by 1, then and diameter big enough, so it must be less than or equal to pi, then it is homeomorphic to Sn. In difference to, say, the topological or now differentiable sphere theorem by the former one, Berger-Klingberg, and then its final resolution by Brändle and Schön. For the Grove-Shiohammer diameter sphere theorem, it's still not clear at all if homeomorphic can be improved to diffeomorphic. But looking at it this way from the point of neighbors and gate spaces, and you could, yeah, if you could solve this question. So this formalism also helps that maybe looking at old questions differently. However, let me stop now. The diameter sphere stream is nothing else, of course, than the stability version of Toponogov's fineness, then carried over by Cheng to Ricci, say, but of Victor Toponogov's famous maximal diameter sphere stream. So, and this is, yeah, let me hope you can still read it. I don't have to read it to you now, but this is a point where I would like to stop, say thank you and spasiba.
Thank you. Is there any question?
A little remark.
Yes.
A little remark, but Toponogov had proved his splitting theorem, published his splitting theorem in 1964, not in 1967, which was on the presentation.
Oh, sorry, maybe I mixed up. Yes, I mean the original paper. It's in the Mathematychesky Svornik, right? And then so the reference I took is then it was translated into German and in the old version of Zentralblatt. Yeah, and then from the Zentralblatt, it was translated into an American journal. Yeah. So thank you very much. Yeah, I will take notice.
And,
yeah, but I should have said it's
Encyclopedic
much
Journal
older.
of Mathematics, it was published in 64. Yes.
Yeah. Thank you.
Any other questions?
Oh,
Maybe.
well, I have one. And then the results of Marcus and the lie, where you mentioned that they approved using rigid flow. Doesn't it also give the homotopy type of the space of metrics or whatever? Not metric, but modular spaces.
Oops. Yes. I'm sorry. Now I have. It's too much echoing. Could you repeat? I understood Coda Marquez and something with the Ricci flow.
At some point, you said that some of the previous results about connectedness of the modular spaces are rigid flows or some other flows. Well, the question is, don't they prove at the same time that the space is contractible, actually, not just connected?
Yeah, I'm sorry. At least I did not get the last sentence. So in low dimensions, there's of course one knows now much more about curvature flows and can use also if you impose stronger curvature conditions, like in dimension 4, if you impose conditions not just say on lower bound on curvature and not as strong as say curvature operator, then there's more known, yeah, especially for biocurvature. But for higher dimensions, sometimes you can use of course the Ricci flow to smooth out things, or if you know you are on a say non-negatively curved manifold with finite pi1, you can use the flow to push it to positive Ricci, for instance, the metric. Yeah, but and so sometimes you use the flow like in dimension 2 uniformization to make things connected. But in general, you of course then are always bound to one component. And what Coda Marquez did was actually using geometrization and Grisha Perelman's work to flow inside the moduli space the metrics to some sort of canonical metric coming from the pieces of geometrization, where he then can stop. Yeah. But I'm not sure if this answered your question or comment. I must admit, I just understood half of it.
Was that they probably proved more. They probably something like the space is contractible or something like this.
If you know, well, Coda Marquez, he has more results for. So, no, I think what you're alluding to now is there's different work by Richard Bamler and Bruce Kleiner. That's where they proved more, but there they were looking at other curvature bounds. So Marquez has, for instance, also result on S3 because you know the diffeomorphism group of S3 for the space of metric, not just for the moduli space. But if it comes to connectedness, of course, lower bounds for the number of components of the moduli space will also give you lower bounds for the space itself. And when you know about the diffeomorphism group, then you can also say for S3 you have connectedness. And S4, as I said, is completely unknown.
Okay. I think we should thank you again. Thank you.
Yeah, thank you as well. It was a pleasure to be here. And
okay, we have slightly more than 10 minutes for a break.
Yeah, we have a coffee break here, and I would like to.
So let me stop share.
Yeah. Hi. I would like to remind about the breakout rooms. So you can see them on the interface or maybe on the mobile. And what I suggest is that the first speaker of the pair, Vladimir, spends a little time in breakout room 1, and the second speaker will spend some little time in breakout room 2. So we come and
try.
well, actually, I want to go into details.
So I should. So, Sergey, I should join room 2.
Yes, let's try.
Okay.
And we have
and
room 2, so I go there and I try to ask my question again. You answered a lot of you said a lot of interesting things, but well, I asked something trivial, maybe. Yeah. Yeah.
Okay. I just don't know how to how to join the breakout room. Is this? I can open it somehow, but
Найди его и переведи просто в другую.
I can do it physically
Вот там что? Нет, все правильно. Видишь? И назначишь.
So I see Wilhelm in room 1.
Назначим просто. Перемести. Давай я переведу.
Да нет, зачем?
Значит, он перейдет и...
Du hast diese Leiste unten.
Ja.
Breakout Rooms ganz rechts. Ich weiß nicht, ob es bei dir auch so ist.
Ja, genau.
Da kannst du
ja,
drauf tippen.
Genau, das habe ich gemacht. Dann tauchen jetzt sogar 10 Stück auf.
Genau,
aber
Platz Nummer 2.
Ja, und
Breakout Room Nummer 2.
Aber aber da müsste ich mich doch irgendwie einwählen können, oder?
Ich glaube einfach tippen. Also drauf tippen.
Okay.
Versuch mal.
Ich tippe und tippe.
Join steht da, ne?
Doesn't let me enter. What doesn't work?
I can move you from admin account.
Yes, sure. Sure. Okay. Yes, now you are invited.
Able to do it yourself. I will.
Okay.
Frank, if you wish, you can share your screen. Maybe it will be more convenient for you. Is it okay? Okay.
There we go. Now I think you can hear me and see me. Although you're all off at the coffee break, probably. Try something. Oh, no. Now I think. Good.
the end, but there he really stops just throwing it to some canonical process. But I think what you are saying is there's more into this work of Bamler and Kleiner. Because Coda Marcus, so he's just interested in positive scalar curvature, and by now I must say scalar curvature is more a thing for topologists, where they can do some spinboard. It's not really. Now they are happy that Gromov does something new there, and they have geometric input. But this is very weak there. And Bamler Kleiner, they look at maybe they also make it a little fancy sounding. They look at what they call the generalized Smale conjecture. And that means you take a manifold, it has usually a huge diffeomorphism group, but if you take a nice metric on it, of course, the isometry group is just a finite dimensional Lie group. And the idea there, what they try to do is you can, it's not always true, but this Smale conjecture says that you can always sort of retract or contract the full diffeomorphism group onto the compact isometry. And that's what they prove sort of for certain three manifolds with say positive Ricci in first a short and then a very, very long paper. But I think this is a place to look at Bamler and Kleiner.
Yes, Bamler did define a very careful analysis of the singularity structure of Ricci form. So he's the only one, in fact, to improve, to significantly go further than Ebermann.
But it's like
that is being used, and that is being used.
Okay, but because Sergei was asking how to also catch the homotopy type that way.
That's different.
Okay, I think I'm ready. My screen is visible. There does seem to be some background noise. Oh, good. There, the background noise has disappeared. And thanks, Bal, for reporting the screen looks okay.
Нет просто никого. Нет никого.
Ну да, как раз можно зайти, как напишешь.
Я просто когда буду хватить компьютер выключите, камеру. Это запомните, да? Ага. И наш микрофон. Да. Когда будете выключать колонки, то они так будут.
Да, прекрасно слышу.
Да. Если вы сделаете это сначала, то
Это сначала.
сначала, да.
Да, как раз сначала я мне вот чуть-чуть.
Ну, ничего страшного, в принципе, в этом тоже нет.
Что там случилось?
Не, все нормально, просто...
То есть вот это же горит, у тебя пилот,
Да. Пилот. Да, можно, в принципе, до завтра.
Okay.
Когда...
It's time to start, I think. Yeah.
Ну и так все слышим, а те...
Да, мы сказали. Окей. Let me introduce Frank Morgan with the parametric problems and densities. Okay, you're welcome.
Thanks very much to you, all the organizers. It's great to be here, at least virtually, in St. Petersburg at this conference in honor of Toponogov. The original isoparametric problem in the plane was just to enclose the area with minimum perimeter. You know the answer is a circle. In fact, that was proved by the ancient Greeks by a symmetry argument, looking mainly at polygons. And more recent symmetry arguments prove a similar result, that the ball is the least perimeter way to enclose given volume in higher dimensions. And also similarly on the surface, on the sphere Sn, on the n-dimensional sphere, and n-dimensional hyperbolic space Hn. And an example I want to emphasize today in so-called Borel space, which is Euclidean space with density e to the r squared. Now this density weights both the prescribed volume and the perimeter that it bounds. So the statement is that the sphere about the origin minimizes weighted surface area for given weighted volume. And the reason you can use symmetrization is because this density, e to the r squared, is also a product, e to the x squared times e to the y squared. One could think about more general radial densities. You no longer can use a symmetrization argument, but the conjecture was that balls about the origin are still the solutions, the minimizers, isoparametric, as long as all of the balls are stable. And the condition for stability, which was provided by Ken Brackey, is that the log of this radial density function is convex. So that's the so-called log convex density conjecture. The easy thing to prove is that it's true for large volumes, for large balls about the origin. And that uses essentially just the divergence theorem, or is how clarified the situation, just looking at the tangential component of the area, of that surface area. And then in 2013, Fagali and Maggi proved the opposite extreme, that small balls about the origin are isoparametric using just asymptotic analysis. That was still 5 years before Fagali got the Fields Medal in 2018. And as editor of the Notices of the American Math Society, I got to attend the press conference there, and they asked him how his advisor, Cedric Villani, received the news, because Villani, of course, was also a Field medalist some years before, and had already become a member of the French Parliament. And when I talked to Villani later, he verified that indeed he was sitting on the floor of the French Parliament when the call from Fagali came with the news, and he had to excuse himself to enjoy that announcement. Well, knowing the two extremes still leaves a lot of territory in between, a big gap for proving it for all prescribed volumes. There was a lot of machinery developed, brilliant new abstract ideas for approaching this problem, but none of them were able to close the gap. And so it remained an open question until a graduate student at the University of Toronto, Greg Chambers, proved it using none of that special machinery, just using hard estimates and comparisons. So the proof is, as usual, starts with symmetrization. And this green blob here has already been symmetrized. You can tell because it meets every purple sphere about the origin in a spherical cap centered on the x-axis. And so it's enough to look at these green blobs, which are already volumes of revolution determined by a planar generating curve. So the problem is really a problem about curves in the plane, but it's a very hard question about curves in the plane. And the analysis looked at this generating curve where it starts farthest from the origin out on the x-axis. And then if it doesn't stay at that distance from the origin to produce a sphere about the origin, but has greater curvature and starts going inward, then you can show it will spiral inward and produce a contradiction. But it's a very delicate argument involving 44 pages of clever comparisons. I asked Greg Chambers when we were hiking in the mountains of Western Massachusetts about this proof, and this is what he had to say to me.
So the proof of the log convex density conjecture first involves reducing the problem down to axially symmetric minimizers and then examining the generating curve. So from a first order formula, you can produce an ODE for this curve, and you can show that if it's not an upper half circle, that's a spiral in too quickly. But what's fascinating is that the estimates involved in proving this are actually very delicate, surprisingly delicate.
So that was a great result. And then I asked my students if they could use similar methods to prove a similar result, not in Euclidean space with that density, but in hyperbolic space with that density. The stability condition is exactly the same in hyperbolic space, that the log of this radial density is convex, but it did not extend easily. They did not get it. The hyperbolic is much harder. I think if I had to give a reason, it would be that in the hyperbolic plane, there's no canonical north, south, east, west, as there is in the Euclidean plane. Now, what would be the most general conjecture? I like to think about that for any radial. I wanted to mention first, yes, here that the 2D case was proved by McGillivray in 2018. And again, it was by analysis of the differential equation. But now I wanted to think about the most general possible conjecture for any smooth radial density and metric. And the naive hope would be that spheres about the origin are isoparametric as long as they are stable. Unfortunately, we know that this can't possibly be true. There are known counterexamples where, for example, an annulus might be minimizing instead of the sphere centered at the pole at the left, even though all the spheres about the pole at the left are stable. But at least you could hope that the isoparametric region has to be rotationally symmetric about the pole. We hoped that was true for a while, and then I found a counterexample to that too, where for small prescribed area in this surface, the minimizer prefers to be not around the pole, but farther away where the Gauss curvature is greater. We know that the small minimizers like large Gauss curvature. The reason it's hard to produce this counterexample, though, is that instability increases with the Gauss curvature. And since the ball about the pole at the top is only marginally stable, you can't allow the instability to increase. So how can you increase the Gauss curvature? Well, the way that it works is that the instability and Gauss curvature do increase together, but the constant relating their rates of increase, Q prime, the instability rate of change, is related to G prime, the Gauss curvature rate of change, by the circumference at that distance from the pole. And so the trick is to let the circumference get large and then decrease the Gauss curvature. And since And now there will be a big decrease in the instability. So now everything becomes very stable. And then when the circumference is smaller, you increase the Gauss curvature to make it a lot bigger, but there's only a small increase in the instability, so you still have stability. So that's the idea behind that counterexample. So then what's the right conjecture? I don't know what the right hypothesis should be. Spheres about the origin are isoparametric with a smooth radial and what? What other condition on the metric and radial density? I don't know. Good open question. Another interesting open question involves the continuity of the so-called isoparametric profile. That is how the least perimeter is a function of the prescribed volume. So that's that isoparametric profile function. It's easy to prove the continuity is easy to prove in compact ambience, or if the ambient has finite measure, or asymptotically bounded geometry, according to Flores and Nardulli in 2020. But in general, there's a potential problem that as the volumes go down to a limiting value, the least perimeter might jump up. So at least in principle, that's a problem. And in fact, it's easy to give an example if you allow variable density. So if you're talking about manifolds with density, as we were with Borel space, here's how you can get an example by taking an infinite sequence. So the union of an infinite sequence of spheres whose unweighted volume, classical volume, is going down like 1 over n, while the density is going up like n plus 1, so that the weighted volume is 1 plus 1 over n, is approaching 1. Now, if you take any of those particular volumes, 1 plus 1 over n, well, you can just take one of these spheres, which has no boundary, no perimeter at all. So the least perimeter is 0. But if you want to get volume exactly 1, you have to cordon off a part of one of these spheres. And it turns out it's cheapest to do on the sphere that has the smallest density. Minimizers like small density on the left. And that has some positive cost. So you get the limit of 0 values jumping up to some positive number. Now the question, I guess, is can you do this with classical manifolds, with unit density? And Nardulli and Pansu showed us that the answer is yes, using some quotients of the three-dimensional Heisenberg group. But the same idea, you still have an infinite sequence of these quotients with volumes 1 plus 1 over n. But if you take quotients of the Heisenberg group and you vary a certain parameter epsilon, they get isoparametrically worse and worse. So that again, if you want to make the tiny adjustment, the cheapest place to do it is on the sphere on the left. And so there's some positive cost to volume 1, even though you can get away with 0 cost for volume 1 plus 1 over n. So you lose the continuity of the isoparametric profile. You could ask, what about 2D? And shortly on the heels of their argument was given a beautiful example using expander, based on expander graphs by Papasoglu and Swenson. And these expander graphs are very highly connected, which means that if you want to enclose small volume, it takes a lot of area or perimeter. Now, of course, these graphs are just graphs, but you can turn them into manifolds by replacing the nodes by little spheres and the edges by very thin negligible tubes. And then a similar argument applies. So that's a beautiful counterexample to continuity of the isoparametric profile in that and in higher dimensions. Here's another interesting open conjecture about convex bodies in Euclidean space of unit volume. So that's our universe right now. We're working in one of those convex bodies of unit volume. And the idea is to cordon off some fraction of the volume, but minimize the interior perimeter required to do that. So you can do this in these various convex bodies. And the conjecture says that the worst place to do it, The worst case is the round ball, that for any particular fraction, it takes more interior perimeter in the round ball than in these other convex bodies, where it's cheaper to do it in some corner or some place where the curvature gets largest. There's no corner inside the round ball. So I had my students look at this too, and oh, this was known only, it's only been proved in the plane in 2D for the case where you want to take just half of the volume. A very special case by a very special argument. It's the only case that's known. My students got some minor results, proving, for example, that the round disk in 2D is worse than any regular polygon. Of course, if you could prove that it's worse than any polygon, you'd essentially have the whole result by approximation. But they just proved it for regular polygons. And they also showed that it was true for arbitrarily small areas in the plane. This is a proof this is a picture of that 2014 geometry group. And you see there in the picture also is Greg Chambers, who I mentioned before for proving the convex body isoperimetric conjecture. The log convex density conjecture. He came to meet with them and consult with them on a different project that I'm not going to talk about today. Oh, there he was. Now, just this year, there was a note appeared about 2 new cases in the plane that were covered. The first case, when you have axis symmetry, and you know that you have just 4 vertices. Vertices are places where the curvature changes sign. There always are at least 4 of them. If there are just 4, they got a proof in that case. Also for smooth perturbations of a round disk. Wang and Wang were able to prove that. So that's the latest news on the convex body isoperimetric conjecture. By the way, the hypothesis that the body is convex is necessary. Otherwise, you could take, for example, an annulus is worse than a round disk because a small area would have to be inconveniently put up against this outer circle that has small curvature, and it's more conveniently placed in the disk where that outer circle has greater curvature. By the way, there's no lower bound on the amount of perimeter required to enclose a given fraction of the volume. By just taking a long horizontal rectangle, for example, you can make that separation perimeter very cheap, but that has large diameter. And actually, you can get a lower bound if you bound the diameter. This is an interesting special case of a beautiful, much more general theorem by Emanuel Millman back in 2015. And the worst case is actually a thin frustrum of a cone, as pictured there in green. Yeah, beautiful special theorem. Okay, well now I would like to focus on optimal tiles. So there's an additional condition I'm thinking about now. And the original question here is, what is the most efficient, that is, least perimeter way to tile the plane with unit areas? So here, in these tilings, each tile has an area, which we're assuming to be 1, and a perimeter, and that's what we're trying to minimize. In each of these tilings, all the tiles are identical, but we'll also allow tilings by mixtures of tiles as long as each tile has unit area. And the answer, the winner, well, is the Bees hexagonal honeycomb consisting of regular hexagons, as was proved by Thomas Hales back in 2001. Circles, of course, have less perimeter, but they don't fit together. They don't tile. When Hales proved this, it was the longest standing open problem in mathematics going back to the ancient Greeks. Hales says proof, actually, to avoid the infinities of the Euclidean plane, starts by taking a large square and identifying the sides to get a compact torus to work on. His first lemma was an easy one, just using Euler's formula, that says on average, the number of edges of each tile, which might vary from tile to tile, on average has to be less than or equal to 6. In the lower right-hand picture there, sometimes it's 8, sometimes it's 4, but on average it's 6. And the proof just uses the Euler formula, which says that on the torus you always get 0 if you take the number of vertices minus the number of edges plus the number of faces. And you can compute that just by adding up the contribution of each tile. Since the tiles meet in at least 3s, each tile contributes at least n/3 vertices. Since tiles meet in 2s along the edges, contributes at least exactly n/2 edges, 1 face. So the arithmetic shows you that on average, n has to be at most 6. The hard lemma is his so-called hexagonal isoperimetric inequality. It's going to be very famous someday, which says that for every tile, we'd like to say that the perimeter P, in comparison with the perimeter of the regular hexagon, P6, is greater than or equal to 1. But of course, that's not true, because one particular tile could be more like a circle. It could have edges bulging out, or it could have more edges than 6. So you have to impose penalties for that. Here, X denotes the amount of area bulging out. And so there's a penalty for that. And if the number of edges is greater than or equal to 6, there's a penalty for that. And this then becomes a true fact, but very hard to prove. Hales used many delicate inequalities that held on certain ranges. And if he couldn't prove it on the whole range, he'd subdivide the range into 100 sub-ranges and prove it on each range, sub-range using computers as necessary. It was quite a feat. But if you'll grant him that lemma, then the theorem follows easily, because you just take that inequality that holds for every tile and average over all the tiles. And now on the average, the amount of bulging is 0, because if one tile bulges out a certain amount, the neighboring tile bulges in by the same amount. And the second term, involving the number of edges, is favorable by the first lemma, which says that on average n is greater than or equal to 6. So we get on average that P is greater than or equal to P6. So that was Hales's proof. Of course, if you knew you were going to use hexagons, regular hexagons are best. Similarly, if you were going to use triangles, regular equilateral triangles are best, although not as good as hexagons. A middle case is quadrilaterals, regular quadrilaterals. The square is best. And for pentagons, the regular pentagon doesn't fit, doesn't tile, has this wicked 108-degree angle, just doesn't tile. So you might think you can't tile with pentagons, but there are lots of ways of tiling, even if you use just a single pentagon. The first type discovered back in 1918, one of infinitely many of that type. And the latest type, the 15th, discovered in 2015. And then that year, Michael Rao announced that he had proved that that's all of them, although the proof hasn't been verified yet. 4 of the last cases were discovered by an amateur mathematician, Marjorie Rice, who learned about the problem in Martin Gardner's column in her son's issue of Scientific American. Well, but what's the winner? Best pentagonal tile? It's a tie between the Cairo pentagon on the left and the prismatic one on the right, shaped like a house, with 2 90-degree angles at the bottom and 3 120-degree angles at the top. The Cairo one on the left has exactly the same angles, although the 90-degree angles are opposite on the left and the right. And how tall do you make the house? Should be circumscribed about a circle, according to a principle of Lullier that goes back to the 1800s. The one on the left is called Cairo due to early old reports of sightings, not in even museums, but in the streets of these Cairo pentagons. So I had to go there to find out, and sure enough, I found beautiful examples at the Al Jazeera Sporting Club of these Cairo tilings. Well, the idea of the proof that Cairo and prismatic are the best tiles, again, starts with Euler, which shows that on the average, there are at least 3 large angles of degree 3, averaging 120 degrees, therefore. And then there's a convexity argument that says it's best to have three of exactly 120 degrees, and the other two have to average, therefore, 90, and it's best to have them be exactly 90 degrees. So that's the idea of the proof. The complication is that you have to consider degenerate cases of quadrilaterals and triangles. And then if you look just at the remaining pentagons, the average pentagon might have 3.1 large angles. And of course, you can't say it's better for every pentagon to have 3.1 large angles. That doesn't make any sense physically. But it turns out you can make sense of it mathematically. You just allow such ideal tilings. And then once you show that it's best for the pentagons all to have 3.1 large angles, you can throw away you can eliminate the triangles and quadrilaterals and return to the earlier case. This was a theorem joint paper with 8 undergraduates, appeared in Notices of the American Mathematical Society. And after we had proved that, I challenged the other students of the world to prove that you couldn't do equally well by mixing the Cairo and prismatic tiles, that just wouldn't fit. Looks sort of obvious to me. And after I sent that out, no sooner had I sent it out, 2 days later, a freshman at MIT sent me uncountably many mixtures of Cairo and prismatic pentagons. So I was completely wrong about that. And the way he did it was very clever. He noticed that the Cairo tiles could be stacked in a diagonal, and similarly, the prismatic tiles could be stacked in a diagonal. And then you could just semi-alternate these diagonals in any way you like. On the left here, they're just simply alternated, one Cairo, prismatic, Cairo, prismatic. On the right, it's one Cairo and then 3 prismatic, and then a Cairo and then maybe 4 prismatic. So there are uncountably many ways of doing that. So I immediately recruited that freshman, Brian Chung, from my 2011 geometry group. It turned out to be a very international group with Brian from Hong Kong, Luis from Venezuela, Miguel's family from Mexico, and Nurali's family from India. And they thought they could prove that Brian's examples were the only mixtures. And then the night before they were given a talk on it, they discovered another, which they called pills, and another. And then they went to Marjorie Rice's webpage, and they found that she even had an example there. She wasn't trying to minimize perimeters. She just thought it was a beautiful example. Here's one of my favorite examples they came up with, so-called spaceship. It has so many beautiful symmetries, not only the horizontal and vertical translations, but you can take every spaceship, like the green ship, onto the yellow spaceship by using rotations as well as translations. This is one of the 17 wallpaper groups, and they actually found examples with 4 of the 17 wallpaper groups and many other symmetry groups, including no symmetry at all, this one that they called chaos, and another couple here that have 3-fold dihedral symmetry. Here's one that I like because it inspired me to suggest to Williams College that for the new Science Plaza, they used this tiling. Well, they said they were thinking about it. They didn't, unfortunately, but at least they used one of these new pentagonal tilings in the new math library. So at least we got that. The students' favorite example was this, they called the bunny one. You can see sort of the ears there up on the top. So that was their favorite. Here's what one of the students had to say about these tilings.
We tried to characterize all tilings by Cairo and prismatic pentagons, but we just kept finding more and more, and with 10 different symmetry groups. Will we ever find them all?
She went on to teach in Jordan and then is working with a tech startup in Palestine. Anyway, later students found more. Here were some by Maggie Miller, who then went on to be a Princeton grad student, won a teaching award, and for her work with the Noetherian ring for women there, postdoc at MIT, and now she's just become a Clay Research Fellow at Stanford. One interesting nagging question, which I've been hiding so far is that all of these results, these tilings are known to be best as long as one assumes that all the tiles are convex. And it seems silly to consider non-convex polygons because they have so much wasted perimeter. They're so far from the regular 5-gon. But it's still an open question whether you might do better by mixing in just a few of those non-convex tiles and making all the others more nearly regular. So here's what one of the students in the group that studied that, my 2012 geometry group, said while attending the Summer Math Fest in Madison, Wisconsin.
This summer, we considered tilings of the plane by pentagons. Last year's geometry group had the best tilings by convex pentagons, but were unable to remove the convexity assumption from their results. We found some restrictions this year on the types of convex and non-convex tilings that might do better.
But the problem is still open, a very embarrassing, still open question, not being able to remove those ridiculous non-convex pentagons. Thank goodness the regular pentagon, which is best of all, is convex. We don't have to worry about that. Of course, when you have 7-gons and above, the angles are quite large and too big to tile the plane sensibly. You'd need to have lots. You couldn't even have all degree 3 angles. There's not room for that. You'd have to have silly degree 2 angles where just 2 of the tiles meet, and you'd have to have tiles be non-convex. So there's that regular 7-gon with that too big 129-degree angle. But if you go to hyperbolic plane, then as polygons get larger, the angles get smaller. And so if you take a larger regular 7-gon, it will have 120-degree angles and be a great candidate for a perimeter minimizer tile in the hyperbolic plane. And a still larger 8-gon would have 120-degree angles and be a great candidate. And a still larger 9-gon would have 120-degree angles and be a great candidate. You notice, since there's no scaling in the hyperbolic plane, it's a different problem for every area. So you really have a continuum of interesting problems with this countable sequence of wonderful candidates. And how many of them do you think are proved? Well, the answer is none. So not a single example in the hyperbolic plane has been proved. I asked my students to try to generalize Hales's hexagonal isoperimetric inequality to hyperbolic 7-gons, 8-gons, 9-gons. They got nowhere doing it until finally they proved that it wasn't even true for large n. So this seemed like a total dead end. So in 2019, I asked my students to focus on a much more narrow problem where they don't consider mixtures of tiles, just the best single tile, and don't look at the whole hyperbolic plane. Just look at some nice quotient, some nice hyperbolic surface, the way that Hales started out looking at the torus, not at the whole Euclidean plane. And sure enough, they got it. It was just published this year that the regular n-gon with 120-degree angles, that whole countable sequence of wonderful candidates, they're all optimal single tiles of closed hyperbolic surfaces if the closed hyperbolic surface admits such a tile, and many do, and even if it doesn't, it provides an excellent lower bound. It's always the best you could possibly do. And the proof then is you have to eliminate these seemingly crazy possibilities of some non-convex 100-gon that would generally meet itself in degree 2 vertices, but still be close enough to a regular 100-gon that it would do better than the regular 7-gon. And very hard, I couldn't see any way to prove this. It took 2 ideas that I was very skeptical about. These 100-gons would fit together in different ways. So the different 100-gons would have different number n of vertices, of real vertices of degree greater than or equal to 3. And they said, just replace each of these tiles by the convex hull of those n vertices. Now n could vary. It could be 100 for some of them. It could be 3 for some of them. But on the average, Euler tells you it's at most 7. These things that you get instead no longer tile. They're no longer identical. They no longer have equal area. They managed to prove that they still cover the manifold. That was the key step. Not easy, not by no means obvious. And then they had to apply a new concavity lemma to conclude that it's best for them all for n to always be 7 exactly. N to always be 7. So here was the concavity lemma. Thank goodness I didn't have to prove this. They had to prove that this quantity here is always negative for all values of x and all values of another parameter p. Oh, but they managed to do it. A couple of them gave a talk about it at the Young Mathematicians Conference, and here's what they had to say.
We proved the regular Kagon with 120-degree angles is an isoperimetric tile of appropriate closed hyperbolic surfaces.
The proof? Take a competing tiling. Look at the vertices of high degree and obtain a collection of convex shapes with controlled number of sides. Then use a new concavity argument to show that it would be better to use a constant number of sides, contradicting the optimality of the regular Kagon.
It was a great proof, actually, and proved much more than I announced. I announced the results for that sequence of areas that correspond to the areas of the regular n-gons in the hyperbolic plane. But there's actually an interpolation to all areas. And they don't have to assume that the tiles are identical. They can allow a mixture of tiles as long as the average area is A. But the conclusion then is just that the largest perimeter, not the average perimeter, but the largest perimeter is greater than or equal to their lower bound. Sadly, the result is still open in the hyperbolic plane. For Hales, it was an easy step from the torus to the Euclidean plane. But the hyperbolic plane grows at such a crazy rate that the most outlandish problems can occur as you go off to infinity. So that problem, there's a great open problem. In fact, in the hyperbolic plane, to close with an even easier open problem, it's not even known if there exists a single tile of every area. So I'll close with that. Thank you very much.
Thanks a lot for this interesting lecture. Is there any questions from internet? Feel free to unmute you. Okay, maybe.
Something happens on the screen, but it's that some chat.
Нет. No. It's not.
Sorry, I couldn't understand that question. If anyone would, if you write a question in the chat, I'll be able to see it clearly.
No, there is no questions in chat. Okay. Let's thank you again. It was very interesting and so beautiful. Thank you. Okay, then we have rest for 8 minutes, maybe 7. Sorry, 7 minutes. Okay,
and at the break, I'll go to the first chat room, the first breakout room.
Yes, after the second.
Yes.
Okay.
After the next talk.
Okay. Yes. Igor Nikolaev, are you here? Yes. Yes. Okay, friend, you can. Okay, Igor, you can share your square if you wish.
Okay. Do you see me? Oh, I saw it. Yeah.
No.
Let me try my mic.
Уля-ля. Игорь Георгиевич не узнал бы на улице, если бы встретил. Будь здоров.
Ай. Так, вот вы сейчас.
Ну, прямо там. Узнавай.
Володя, я вас тоже не узнал.
Александр Андреевич, я первых 3 лекции думал, вы не вы.
Дело в том, что... Ну ладно, я потом скажу.
А вот, голубятник. Да. All right. Ага. You can hear me, right?
Yeah, we hear.
Окей. Потому что... Окей. Бэй! Что за елки-палки?
Меня, Александр Андреевич, меня смутил ваш псевдоним.
Дело в том, что я сейчас в Америке, и я внука компьютер. И он игры его использует. И я сначала плеер должен, а потом уже свой Gmail. Ну и выдался не Абариченко, а выдался плеер.
Я так и подумал, что это не ваш, наверное.
Нет, ну...
Так, сейчас посмотрим. Что ж такое?
А чего не слышишь, не видишь? Не можешь свою презентацию включить?
Да, ну еще время есть у нас, да?
Есть. Демонстрация экрана.
Да.
Вот так. Так что я здесь...
Может быть по-другому, Владимир Петрович.
Да, там у них английские подписи, ну да.
Даже не в этом дело, а дело в устройстве зума. Он
Ничего, нормально, я тут входил вроде бы, все. Свой зум, так сказать, испытывал на связи с Харьковом. Женя, ты выше голову, у тебя что-то только...
Так, раз, два, три.
Да у меня такое расположение компьютера, что не видно.
Да, а теперь видно.
Надо наклонять экран.
Да?
Подходит.
Ага.
О, все хорошо. Вполне узнаваемый.
Ну, пока еще.
Вполне узнаваемый.
Дайте-ка я почищу сейчас. Так. And you can hear me, right? Yeah.
Yeah, we hear.
We hear, but didn't see any slides.
Slides now. Slides, share screen.
Okay.
Now everything.
Now you see it, right?
Yes.
Okay.
We have 3 minutes for a break, and then.
All right. I'm ready. Standing by.
Игорь Георгиевич, давно хочу спросить, а шампань это какое имеет отношение к тому, что, к чему мы обычно прилепляем это слово?
Но он пишет по-другому, пишется. Это к шампанскому не имеет никакого отношения. Я даже не знаю, почему он назвали вообще. Честно говоря. Приятно всех видеть еще. Вот Женя подсоединился, я вижу.
Здравствуйте, Игорь Георгиевич. Это еще я решил подключиться. У нас ночь, поэтому я в таком темном виде.
Ну ничего, а я начинал в 3 часа утра.
Это супер палка.
Ну, я уж выключусь опять, чтобы не напрягать связь.
Не понял, какая ночь? Сейчас 18:40, что, 4 часа? Ну, еще
Нет,
11.
У нас
Еще...
почти 10 вечера.
Ну, так.
10 вечера почти что, да нет, уже темнеет рано.
Ну, так
Уже
темнеет,
всё.
это вопрос другой.
Ну да, я про то, что темно. Что я под какой-то лампочкой сижу.
Если перестал видеть.
Okay, well, let's start. I would like to introduce Igor Nikolaev with Alexander Skavich of metric space via Cauchy-Schwarz inequality. You're welcome.
No, first of all, I would like to thank the organizing committee for inviting me to this conference and for giving me the opportunity to talk about my research and the opportunity to honor and remember our late and dear colleague, Viktor Andreevich Stepanov. The title of my talk will be Alexandrov Curvature, Metric Spaces, via Cauchy-Schwarz inequality. First of all, I remind notion of Sasaki distance. Suppose that Rg is C2 smooth Riemannian manifolds, minimum what you typically ask. And U and V tangent vector to R at points A and B. And then we assume that A and B are sufficiently close to each other. And we translate vector U, Levi-Civita parallel translation to point B, and calculate norm of U prime minus V. Then Sasaki distance S of UV will be square root of distance squared between AB plus norm squared of U prime minus V. Now we observe certain properties. What is obvious? Of course, Sasaki distance is positive definite. Of course, it is symmetric. No, and triangle equality need not be true. It is quite obvious in this situation. So, in the terminology of Carl Menger, it is called semi-metric. No, some people call it pseudometric and vice versa, but Menger called when triangle equality fails, it is semi-metric. Well, and of course, we assume that points tails of U and V close to each other, sufficiently close to each other. Well, now we can use lower length functional to define the lower length of a curve in the symmetric S. Now, you see in metric space, you take supreme of inscribed configurations, right? But, or you can take limit, which exists. But in symmetric space, limit, of course, doesn't exist. And you can take either upper or lower length limit, and I can see the lower limit. It's a bit more convenient here. And then we introduced induced distance, which I call S induced, on the tangent bundle T of R, which measure the distances between a pair of tangent vectors as infimum of lower lengths of curves joining these two vectors. It turns out that in C2 Riemannian manifold, this induced distance S induced will be metric, and it coincides with so-called canonical Sasaki metric, which was introduced in 1958 by Sasaki. It is classical object, everybody knows what it is. Now we return to general semi-metric space, and we want to construct analog. We want to extend Sasaki metric to semi-metric spaces. So semi-metric space, even not without geodesics. What do we need? We need substitute for the term norm
of U prime minus V. But it requires parallel translation, and it is really a long shot to expect a parallel translation in general metric or symmetric space. So all we need then metric substitute for cosine of the angle between U prime and V. And we will find such substitute, and we will call it quadrilateral cosine. The basis of the definition of the quadrilateral cosine notation will be Cosca. No, by the way, name, I used to name it HLN function H, but David Mike Worcester introduced this name. And it's the full engineerization of the cosine formula in Euclidean space E3. So if you have two vectors, A, P, and BQ, then it is not difficult to calculate cosine of the angle between AP and BQ, and it will be diagonal squared plus diagonal squared minus side squared divided by 2 times length of norm of vector AP, norm of vector BQ. Well, now we extend this concept to Alexander metric spaces or symmetric spaces in general. We call an ordered pairs of points in a metric space bound vector. So bound vector is ordered pair of points. And we use notation like we used in university probably, right? U is equal AP, V is equal BQ. And we consider pair of non-zero bound vectors in N such that A is not equal to P and B is not equal to Q. And then we define quadrilateral cosine cosq of UV by the following formula. No mystery here. Cosq of UV will be D squared plus F squared minus B squared minus A squared divided by 2xy. Well, let me show you a little bit longer. So this is formula for cosq of UV. In general, cosq can be considerably greater than 1. In LP spaces for P greater or equals than 1, but less than 2, cosq can be as large as you wish. Now, but anyway, we define so-called quasi-inner product between each pair of bound vectors, and we just mimic definition of inner product as long as we can. For every pair of bound vectors U, which is AP, and V is BQ, quasi-inner product is defined, no wonder, it's norm U, norm V times cosq, if norm U and norm V is positive, and 0 otherwise, of course. And the norm of U, of course, distance between A and P, and norm of V obviously is distance between P and Q. Certain bound vectors can be added in the natural way, no head to tail. So if you have vector U, and vector U has tail and has head, and head of vector U at the tail of vector V, then W is sum of vector U, bound vector U, and bound vector V. Now, in my sketch, there are geodesics, but you need only ordered pair of points, not more than this. And we call ordered pair of vectors U and V admissible if head of U is equal coincides with head of V. All right, the set of all admissible vectors will be AN. No, and operation of addition, I already explained, W is U plus V. Finally, we consider properties of quasi-inner product. For quasi-inner product, you can define general quasi-inner product, and then to prove that actually there is unique quasi-inner product in a symmetric space, it is a function from Cartesian product of bound vectors into real line. It satisfies the following condition. First of all, quasi-inner product UU will be rho squared of PQ, of course. It is symmetric. And then quasi-inner product minus UV is minus quasi-inner product UV. And more important, that if VW ordered pair of vectors is admissible, so we can add them together, then quasi-inner product U times V plus W will be sum of quasi-inner products. Now, this is in symmetric with quasi-inner product, we call it quasi-linearization of symmetric space M rho. Now I will state one of the most important steps in our proofs. It's called averaging principle. It plays fundamental role. And suppose U1, U2, Un, and V1, V2, Vn be bound vectors, so that in a symmetric space, so that neighboring vector Uj plus 1 can be added, they're admissible. And the same goes for Vk and Vk plus 1. Well, if U is sum of Uj and V is sum of Vk, then quasi-inner product UV will be double sum of Uj Vk. No, so it is not extremely difficult, but it's quite useful property. Now here is illustration. This is vector U. This is V2 and V1. V2 plus V1 is V. And you can see that quasi-inner product UV will be sum of quasi-inner product. So averaging principle, we use it extensively. Now, essentially, if you consider global configuration, you can subdivide it to small configuration, use averaging principle, and then do what you want to do. Now I would like to slightly discuss a concept related with Alexander's problem. This is not topic of my lecture today, but I think it's useful to mention to explain where this definition came from. So first we begin with extended Sasaki metric and generalized tangent bundles for a symmetric space. Well, of course, bundles, not really bundle, yes, but let's see what it is. We begin with the following remark. So if U and V is a pair of vectors in Euclidean space, then norm of U minus V, it will be, can be calculated, obviously, as supremum over test vectors. Model norm of theta is equal to 1 of absolute value of difference of dot product or inner products U theta minus V theta. So then it's hints how we can generalize this to semi-metric or metric spaces. So you replace inner product with quasi-inner product. Take Alexandrov introduced notion of tangent element. It is direction, class of equivalent curves which form the same zero angle at the same point. It's pair of a direction and reposits non-negative real number which represent magnitude of this norm of this vector. And T of M, so we can introduce quasi-inner Sasaki symmetric. Next on T, we call it T tilde of M later. Symmetric specify extended pseudometric S induced on the set T tilde of M of all tangent elements of M. I repeat, the tangent element is pair of direction. It's kind of generalization of vector of unit length and non-negative number which represent norm. And direction is class of equivalent curves which form zero angle at appropriate point. Also, you can ask why T tilde. It will be clear in a moment. it is really easy to prove that it is triangle inequality holds, but unfortunately it degenerates and it's not positive definite. So it's pseudometric. But luckily, Sasaki distance, which we constructed, can degenerate only on a fiber of T tilde of M. In other words, if S tilde induced is equal to 0, then it follows then two corresponding tangent elements have the same tails. So they're at the same point. Now we defined generalized tangent bundle T of M of a symmetric space by identifying all pairs of tangent elements at a common point having 0 distance S induced between them. So we just glue together all tangent elements which has 0 distance, but vectors are different, right? And we obtain T tilde, T capital of M, which is construction of tangent bundle with S induced on M. And we denote resulting distance in T of M by S induced. S induced will be extended metric. Extended means that metric can take infinite values, but otherwise it's metric space, positive definite, symmetric, and triangle inequality holds. Now, I don't want to, again, to get into details, but I just show one sketch which illustrates notion of tangent bundle. And this is graph, T-graph. Now, T-graph, it's a line with attached ray somewhere to a point in the line. So this is graph. And then construction, which I discussed, produces this sketch for tangent bundle quote in of the T-graph. So this is construction. Now, what is important that construction of tangent bundle, yeah, it may be useless, but it is applicable to any semi-metric space. No, it's like, for example, take upper angle. Yes, upper angle exists for every metric space, right? And sometimes it doesn't give much, but you can use it in any metric space, right? Now I briefly mention Alexandrov problem on metric characterization of regular Riemannian manifolds. Now, a long time ago, I remember a conversation with Alexander Danilovich, and he told, yeah, it's good. Now we know that Alexander spaces of two-sided bounded curvature, they are almost Riemannian spaces, but what about classical Riemannian spaces? And what's classical Riemannian space? It's continuous curvature, so it's C2 Riemannian space and higher, right? Can we characterize them exactly, pure metrically? And first, it probably we should mention Wald, Abraham Wald, who answered this question in two-dimensional case in 1935, and since then there was no progress here for higher dimensions. No, and let us discuss what we can say here. So we prove that for C2 Riemannian space, S tilde induced actually will be S induced, so no degeneration. It is not exactly obvious statement. It took me a while to do it. And then T tilde of M will be T of M. Now, you define curvature, it is really easy to define sectional curvature as limit. You use Alexandrov theory, Alexandrov language, and define sectional curvature. Section will be certain limit of contracting triangle, geodesic triangles. But problem is, it is easy to define continuity from point to point, but not of section. How you define continuity of curvature relative to the section. And here, Sasaki distance enters the game, and we define continuity of curvature relative to sections and point using Sasaki distance. And solution of Alexandrov problem is given by the following theorem. Locally compact metric space with intrinsic metric and Hölder continuous that with X point alpha to 0, 1, of course, curvature, which has local geodesic extendability. No, it means that if you have geodesic short, minimizing geodesic, you can extend it a little bit somehow. Is isometric to SC2 alpha Riemannian mean. No, local compact plus intrinsic, of course, produces geodesically connected. Any 2 points can be joined by geodesic, but no, this is statement of the set. Then we iterate and we obtain pure metric description of CM alpha Riemannian manifold for M is equal 3, 4, and so on, and finally infinity. Now this gives, I hope, complete answer to Alexander's question or Alexander's problem, and kind of, closes this question problem. All right. Now we turn to metric spaces. From now on, I describe our joint result with my colleague and friend and long-term collaborator, Professor I.T. Berg. Everybody calls him David. And what do? We introduce the following conditions for metric space M-row. First is Cauchy-Schwarz inequality condition. Remember, we have quasi-inner product. Well, Cauchy-Schwarz inequality condition states that modulus of inner product ABCD must be less or equal than norm of AB, norm of CD for every pair of non-zero bound vectors AB and CD. Now, of course, Cauchy-Schwarz inequality condition can be written in equivalent form. It's called 4-point Kosovo-K condition that always Kosovo-K of AP and CD is less or equal than 1. Now, for K is equal to 0, which is Kosovo case, it is trivial to prove that is always Kosovo less or equal to 1, then automatically always Kosovo greater or equal than -1, and so automatically Kosovo modulus of Kosovo, absolute value of Kosovo less or equal than 1. So essentially this or that is equivalent to this condition. So here it is not big mystery. And finally, we introduce more sophisticated condition. So if Kosovo condition holds, or actually Schwarz inequality condition holds, then the following Euler's condition definitely holds. But converse requires a lot of work, or it requires work. So it is Euler's inequality condition, but nowadays it's also known as Perf-Inflow's Duralnidis condition. Perf-Inflow is a very brilliant mathematician who used it to study groups and apply some geometry. And why did we decide to change name of this inequality? Problem is that Euler proved, obviously many years ago, equality in Euclidean space, surprisingly, and this equality immediately implies inequality about which I'm going to talk. So it is Euler's inequality condition. And it states that sum of squares of diagonal is less or equal the sum of squares of sides. Now here on my sketch you see geodesics. No, you don't need geodesic. All you need is quadruple, ordered quadruple of points. And then this is Euler's inequality condition, or Inflow's Duralnidis condition. All right. Now I remind you what is a zero domain. Nowadays, everybody, but me probably, uses the name cat of zero space, and these are identical. But in case you forgot, it is convex subspace of Alexandrov space approaching less or equal to zero, with geodesic segments minimizing geodesics, depending continuously on their ends. So cat of zero equals R0 domain. Now, it is original Alexandrov's notation name. No, and R stands either for domain, or you can attribute to Riemann, which seems to be natural here. So main theorem, a geodesically connected metric space is in a zero domain if and only if it satisfies the 4-point Kosztola-K condition. So necessary and sufficient condition is Kosztola-K condition or Cauchy-Schwarz inequality, whatever you feel free. No, first, this is kind of trivial corollary. Now I remind you that symmetric space weakly convex. Now, let me show you, I don't want even to read this. Intuitively, if you have 2 points, then you're saying that although you cannot claim that there is point in between, so sum of distances will be equal to the distance between 2 initial points, but approximately this is true. This is what these inequalities say. Cauchy sequences, symmetric spaces quite sometimes can be ugly, but they are defined in the same way as in metric space. And corollary states that symmetric space M rho is isometric to a complete A0 domain if and only if the following conditions satisfy. M rho is weakly convex. Every Cauchy sequence in M rho has a limit, and M rho satisfies the 4-point Kosztola-K condition or Cauchy-Schwarz inequality condition, if you like. No, there is not much mystery here. If M rho satisfies 4-point Kosztola-K condition, we can prove that semi-metric actually is metric. Then it is just complete metric space. And if it's weakly convex, well-known old Menger theorem, Karl Menger, states that it is geodesically connected, and we are done. Second corollary is more sophisticated, and it requires averaging principle. This is where we use it, which enable us to prove much stronger result. Theorem, geodesically connected metric space is an R0 domain if and only if it satisfies Euler's inequality condition. So necessary and sufficient condition is Euler's inequality condition. In addition, if M rho is geodesically connected metric space with Euler's inequality condition, and Q, which is ordered quadrupole ABCD of distinct point in M, for which the equality holds in Euler's inequality, that is, sum of squares of diagonals rho squared of AC plus rho squared of BD is equal rho squared of AB plus rho squared of BC plus rho squared of CD plus rho squared of ED, then the geodesic convex hull of the set ABCD is either isometric to a parallelogram in the Euclidean plane or a segment of straight line. Now, here I should mention at least that SATA, when we published our paper, very soon we obtained a message from SATA who informed us that he had another proof, and much shorter than our proof, we should admit, and purely manipulation with metrics. And yeah, it's a good proof. Yeah, but we kind of at some point were inspired and hope to apply Sata's method to non-zero K. Unfortunately, it turns out that Sata's method also uses implicitly averaging principle, and without averaging principle, no, it is a problem. Yeah. No, and Lafont and Prasidis published paper where they, before us, where they prove that if it is R0 domain, then Euler's inequality holds, but converse part definitely was not known. Now, more new material, it is non-zero K. So recall that K plane Sk is Euclidean plane if K is equal to 0. Open hemisphere of radius 1 over square root of K if K positive. And the hyperbolic plane of curvature K if K is negative. Now we define K space S3K absolutely the same way. So definition is similar. Now generalization of the quadrilateral cosine to non-zero K is not straightforward. It's not as straightforward as for 0. And here we need construction. Now we begin with introduction of certain notation. We will use elementary complex analysis notation. Let K capital be not equal to 0. Kappa in what follows will be square root of absolute value of K capital. And then K hat is equal kappa, which is square root of K if K is positive. And if K is negative, kappa hat is I times K. So I is square root of -1, which is I times square root of -K. Now, we consider K space. We assume that P is sufficiently close to A, Q is sufficiently close to B, and this is geodesic segment, and this is midpoint. We consider vector U, which is exponential -1 at point A of P. So U is tangent to this geodesic, and norm is equal to arc length of this geodesic. And the same goes for V. V is exponential -1b of Q. U prime this time will have slightly different meaning. Remember, in the past, it was a result of parallel translation of U to point B, right? But now I decided to use notation U prime for vector, which is minus vector, which is a result of parallel translation of U to point B. And we want to calculate cosine of minus U prime. Minus U prime will be exactly parallel to U, and V. And this is what we need to construct COSPA. Well, if you open old book by Elie Cartan, Geometry of Riemannian Spaces, you may find geometric description of parallel translation. So it takes some, no, I modified it, Cartan's construction slightly. And if you look at this sketch, this is midpoint. And if you reflect symmetrically point P with respect to O, and the result will be point P prime. If P is close to A, it's always is possible. What does it mean reflect symmetrically? That length of this geodesic is equal to length of this geodesic, and this is geodesic, right? Then you obtain that vector U prime will be minus vector parallel to vector U, right? But cosine of this angle will be minus cosine of the angle P prime PQ. And now after a series of application of spherical or hyperbolic cosine formula, you obtain the following formula for non-zero K. Here I repeat all of this. It will be cosine of K hat P plus cosine of K hat X times cosine of K hat Y divided sine of K hat X, sine of K hat Y minus similar expression. Let me not to read it. I will read on next page for K positive and K negative. So if K hat is positive, cosine will be cosine. But if K capital is negative, then kappa, yes, kappa hat. Kappa will be I kappa, right? And we know that cosine will turn to cosha, which is hyperbolic cosine, sine turn to sinha, multiplied by I, sine is hyperbolic sine, and we will obtain corresponding expression. So we mimic this formula and take it as formula for K quadrilateral cosine in semimetric space. So suppose from now that M rho is a semimetric space, and then cos quadrilateral K quadrilateral cosine of AP and BQ is defined by the foregoing formula. Now, of course, we got to assume that distances between AP, BQ, and AB less than pi over square root of K, otherwise we divide by 0 sometimes for positive K. Now, before I write formula in the general metric space, more absolute value of cos square K can exceed 1. And what is our goal? Loosely speaking, we want to show that Alexander's upper curvature condition of a geodesically connected metric space can be characterized in terms of polynomial inequality if K is 0, and trigonometric or hyperbolic trigonometric inequality, polynomial inequality if K is not 0. Of course, inequality involving 6 distances of independent quadrants. Now, if K is positive, we assume that X, Y, and A less than pi over square root of K for K positive. This is A, X, Y, and this is A. And then, if K positive, we obtain that cos square K will be cosine of kappa B plus cosine of kappa X times cosine of kappa X divided sine of kappa X, sine of kappa Y, minus cosine of kappa X plus cosine of kappa D times cosine of kappa Y plus cosine of kappa F divided by 1 plus cosine of kappa A times sine kappa X, sine kappa Y. Now, if for K negative, you replace cosine with cosha, sine with sinha, and multiply by -1. You let me not to read it. This is expression for cosha. You can ask me what in the world you can derive from this. These are not simple trigonometric expressions. No, typically, sometimes we can derive something, but most of the time we use comparison, of course. We use geometric construction, comparison. All right. No, and for completeness, 0 quadrilateral cosine by definition is constant. Now we introduce similar condition, you will be surprised, for K not equal to 0. Cos square K APBQ less than or equal to 1. It is the upper 4-point cos square K condition, always. With subject to restriction in positive K, let me not repeat it. Lower 4-point cos square K condition, cos square K always greater or equal than -1, All right, and subject to certain restriction when K is positive. I am not repeating it. And we say that a rho satisfies the one-sided 4-point Koszler-K condition if it satisfies either the upper 4-point Koszler-K condition or the lower 4-point Koszler-K condition. Now, here we will discuss this in a moment, but situation is more complex. Unfortunately, it is not true that if always Koszler-K APBQ less or equal to 1 in general case, then always Koszler-K APBQ greater or equal than -1. For K0, it's true, but for K non-zero, it is simply false. Well, we have to say something about that. We will postpone it, keep it for later. Main theorem, it resembles main theorem for K is equal to 0, but there are problems also here. Let K be not 0, and let M rho be geodesically connected metric space, such that diameter of M is less or equal than pi divided by 2 square root of K, when K positive. Then M rho is an RK domain with the same diameter restriction if and only if M rho satisfies the one-sided Koszler-K condition. Now, let's make remarks. Lack of linearity for non-zero K, so lack of averaging principle in the model space presents substantial conceptual technical problems. So we really have to come up with other proof, and we present new probably comparison tools, etc. If K positive, so you see, mysterious is this estimate of them. Why in the world it is less or equal than pi divided by 2 square root of K. But if K positive, then it is possible that absolute value of Koszler-K is greater than 1, even in RK domain. Oh, by the way, RK domain, it is domain, convex domain of Alexandrov space of curvature bound above by K, where geodesics depends continuously on their endpoints. And it is not always equal to ket of K domain, because ket of K sometimes defined differently. But subject to this restriction, here RK domain is equal to ket of K domain. Equal. So in RK domain, it's possible that modulus of Koszler-K is greater than 1. No, of course, if diameter of K is, unless diameter of RK is not greater than pi divided by 2 square root of K. But what is interesting that in K space, always absolute value of Koszler-K less or equal to 1. Typically, you expect that whatever you have in K space holds, goes for RK domain. Unfortunately, this is not the case. No, and we were lucky enough to construct counterexample and to show that restriction on the diameter of M rho for positive K cannot be dropped, and the diameter bound on the hypothesis of the main theorem is sharp. So this condition must be here. That's the moral of the story. Well, now one would expect to state K Euler inequality, Euler's inequality K condition, and prove similar result. We cannot do it because there is no averaging principle, although emotionally we believe that probably it is true, but we cannot come up with proof, and we don't know if K or analog of K Euler's inequality characterize RK domains. we offered an extension of K-Euler's inequality to K non-zero. And we proved that in our K domains, it is true, it holds. But a converse statement so far is unknown. Now, corollary. Suppose that K is not zero, M rho is geodesically connected, such that diameter of M is less or equal than pi over 2 square root of K when K positive. So it's absolutely the same as in this area. Then M rho satisfies the upper 4-point cost of K condition if and only if M rho satisfies the lower 4-point cost of K condition. Now, this is not trivial statement because actually what we did, we cannot prove it directly. We prove that if cos square K less or equal to 1, it is our K domain. And we prove that if cos square K greater or equal to -1, it is our K domain. Therefore, both of them must be equivalent to each other. So filter one condition through main theorem and obtain equivalence to the other condition. So, and let me state remark that in a non-geodesically connected metric space, we have example that the upper 4-point cost condition is not equivalent to the lower 4-point cost condition. So it's more difficult. Now you can say that if Cauchy-Schwarz K inequality condition holds, if modulus cos square K is less or equal to 1, then it is our K domain, right? But what if equality sign holds? In Hilbert space, or more generally in inner product space, equality holds if and only if appropriate vector will be collinear, right? Let's see what we have here. Recall that polygonal curve APQBA in Riemannian manifold is called Levi-Civita parallelogramoid if the distances from A to B and from B to K are equal, and vectors which are exponential A minus 1 of P, exponential Q minus 1 of P, are Levi-Civita parallel along geodesic schema. So you consider this quadrangle, and AP is equal PQ, right? And this is corresponding vectors U and V. Then norm of U is equal norm of V, and they are parallel. This is Levi-Civita parallelogramoid. No one can find this definition in Cartan's, early Cartan's book, Geometry of Riemannian Spaces. Now, we slightly generalize, it's not a big deal, this definition of Cartan, and we introduce Levi-Civita trapezoid. We say that polygonal line APQBA, see previous sketch, is Levi-Civita trapezoid if is a vector U exponential A minus 1 of P, or and V exponential B minus 1 of Q, or the vector U and minus V are parallel along the geodesic segment AB. So norm of U may not be equal to norm of V, but they must be collinear. Convex hull nature of in SK of Levi-Civita trapezoid naturally is called trapezoidal domain. No, and trivial remark that geodesic is clearly it's degenerate Levi-Civita trapezoidal domain. Now we state the following extremal theorem for K when cos square K is 1 or -1. Remember that for K is equal to 0, we had some statement which is equivalent to this, the same one. No theorem. Suppose that K capital is not 0 and M rho is geodesically connected metric space such that diameter of M is less than pi divided by 2 square root of K, if K positive. So in main theorem it was less or equal, but now it is less. We have to discuss this. If M rho satisfies the 1.4 cos square K condition, then 1040, right? we obtained that modulus cos k is equal to 1. Oh, it looks like I am approaching to my end. Now, this theorem is exactly the same as statement that equality sign in Cauchy in Cauchy-Schwarz inequality. So two vectors will be collinear. No, and finally, we don't have time for this, but let me just mention this, that all these statements solve Gromov-Kovachev problem in context of Alexander spaces of Kovachev bound above by K. And no, Gromov-Kovachev problem, let me, it's 40, right? So I probably have to finish. No, so if you equate, probably most of you know what is Gromov-Kovachev problem, but Gromov defined global K-Kovachev class, and we define K-Kovachev class by condition on a symmetric matrix with non-negative entries, with 0 entries on diagonal. And condition will be similar to as if cos square k is less or equal to 1, or cos square k greater or equal to 1. No, and then we define classes Mg and Ms, and Mg consists of classes. Let me show you. So it's class of geodesically connected metric spaces satisfying this inequality, subject to this condition. Well, this is just cos square less or equal to 1, right? Multiplied by common denominator. MS symmetric space, here we add that Cauchy sequences converge, etc., right? And this is convex, weakly convex. And then we prove that X row in Mg, respect in Ms, is in the global K plus minus Kovachev class if and only if X row is an arcade domain. So we describe arcade domains as Gromov K Kovachev class. Now I remind you again that K capital of K squared with the upper index plus, it is just cos square K less or equal to 1. Now I think I should be finishing. I'm very sorry that I kept you a couple of minutes extra. And let me stop at this point and thank you for your attention.
Thank you. Is any question from internet? Maybe. Feel free to unmute you and ask. Maybe from here.
Well, my brother, do you hear me? I have some issues with this microphone on wall.
Issues, I cannot hear you very well.
Oh, well, so you started with this Sasaki differential geometric construction.
Yep.
Which is, well, can be used to define a parallel transport of Levi-Civita parallel transport along geodesic, right?
Yes, you need parallel translation.
Can you bring that to Alexander spaces or cat spaces or whatever? Can you define parallel transport of tangent cones or whatnot?
We actually, yes, I can answer this question. Yes, we thought about this, but no, you say never say no, but it looks to me quite definite that no, you cannot introduce parallel translation. It has really weird properties. You can define, for example, that using cos square, but unfortunately, it has so weird properties that you abandon it. No.
I see.
Maybe somebody else will do it, I don't know.
Thank you.
Thank you. Thank you again. If no questions, let's thank again. That's all for today.
Yeah, so we leave this Zoom stuff running for some, well, I don't know, maybe.
Will we go to breakout rooms?
So?
Will the speakers go to breakout rooms?
Yeah, we can. If it, well, it's actually late evening, but if anyone wants to gather in any breakout room, we will keep it running for some time.
Okay.
But how long? I don't know.
7 probably, for 15 more minutes.
Yeah, maybe for 15 more minutes. Yeah. We cannot leave it running overnight. I mean, all this select stuff. So
I promised I'd go to breakout room 1 for briefly now.
yeah, let's try it. Okay,
What is about this? Yep. На 15 минут еще.
Right.
Do you want me to go to break room 1?
Yeah, the idea is that well, one can actually see if you push the button of breakout rooms, you can see who is where.
Yeah, I thought you said you wanted me in breakout room.
First speaker of a pair goes to breakout room 1, and the second speaker of, but it's not mandatory. Well, anyway, everyone will see where you are, but basically, but generally. I can move you there, and well, I don't see anyone.
Because I push the button. I see.
Doesn't work?
I push button, but it doesn't, nothing happens.
Да, этот самый, кнопка join там не работает, да?
No, I open breakout rooms. I see breakout room зал 1. And now I guess I...
А если промотать мышкой пониже, там же их много.
But you're talking about 1, right?
Нет, это будет 2.
Вы хотите, чтобы я был 2, да? Ну, давайте 2. Так, ну, давайте попробуем. О, я клик...
Не работает, да?
Зал 2. Зал 2.
Ну, я могу ткнуть. Я могу назначить. О, успех. Нет, не успех.
Нет, успех. Что такое?
Да.